Our next talk is by Alex Lubotzky, from who will tell us about locally testable good codes. He just entered the waiting room, so he's also going to share his screen, I hope. Alex?
I'm back.
Okay. And you're going to share your screen again?
Yeah, let me do. I don't know what happened. Just a second. Yeah, let's see. But now I lost the appropriate screen. Just a second. Just a second. Okay. You suggested me to do some.
Should be in the middle of your screen on the bottom.
Just a second. What?
In the middle of your screen, but on the bottom. Put your mouse on the screen.
Okay. Yeah, here we go. Is it okay now?
It is good. I see your slides. Once again, locally testable codes, Alex Lubotzky.
Thank you very much. This is a joint work with Irit Dinur, Shai Evra, Ron Livne, and Shachar Moses. Thank you for inviting me. I will try to make it. I have what to say about Shimshon Amitsur. Was really a role model for me and for many of us in Israel and all over the world. I'll try to come and say something tomorrow, and I will start my talk. My talk today is about a problem in the area of error correcting codes. I don't want to assume any knowledge, so let me really start from scratch. Let FQ be the field of order Q, and usually we really care about Q equals 2. And NKDQ code, if Q is 2, then the tradition is to omit the symbol Q. And NKDQ code C is a subspace of FQ to the N of dimension K, and distance at least D. So let's see what we mean by that. Basically, we have K bits of information. We encode them into FQ to the N. N is larger than K, and we want them to be spread around from each other. Why? Because the story is, as you can imagine, that the sender is going to send N bits. Only K of them are really meaningful information, but he wants that the receiver will be able to correct mistakes if mistakes are happen, and if there is a good distance between the code words, then mistakes can be corrected. Now, what is distance? Distance is simply the Hamming distance. The distance between two vectors, alpha and beta, is the number of it's simply the number of bits. The Hamming distance means the number of bits in which they are different. Now, because we will talk today only about linear codes, namely that this is a real subspace, then if alpha and beta are in the code, then alpha minus beta is also in the code, and 0 is also in the code, then you can see that this is the same as the minimum Hamming weight of a vector alpha in the code, which is not 0. Now, but we are not engineers, we are mathematicians. So what we care is about the case where n is going to infinity. In the early history of the subjects, starting with Shannon, this always was the attitude of mathematicians, but I think the engineers, at least those friends of mine, used to laugh at us because, you know, they care about n equal 128, 256. Who cares about n going to infinity? But in recent years, even in practical application, n starts to be something like 200,000, and that's a better approximation to infinity. So it starts to look like these considerations are not completely stupid. Anyway, a code. Now, I will use a tradition to say a code, but we always mean by that a family of codes when n going to infinity. A code is good in the sense of Shannon. Shannon was really defined what is a good code, and he kind of set out the golden standards of coding theory. We say that the code is good if both K, which is the dimension of the subspace, and the distance of the subspace grows linearly with n, namely, if there exists an epsilon such that K is more than epsilon n and D is more than epsilon n. And usually the coding theory people like to say they take the rate to be K over n. So we want K over n to be bounded away from 0. And the normalized distance is D over n, and we want it to be bounded away from 0. Now, the feeling is, I mean, I think it's, you can see easily, you can think about it easily and see that they kind of, there is a kind of a competition with each other. I mean, you can expect that if the dimension of the code of the subspace is very large, you cannot expect the distance to be very large, and vice versa. And basically, there is a very simple inequality, basically saying that the rate plus the distance is at most 1. And there are more delicate inequalities, which I'm not really going to talk about. So anyway, in the terminology of this area, they usually say we want constant rate and constant distance. What they mean is normalized distance. Now, it's not at all clear. It's not at all clear that such code exists. I mean, it's really not clear because they kind of compete with each other, as I explained. And Shannon was the first to consider this. In fact, he proved that they exist by what was at that time a very new method. I'm not sure whether he invented that method or Erdos invented that method for random graphs, whether they influence each other, whether they knew about each other work, but approximately at the same time, when Erdos started this random graph, we became a big theory. Shannon proved that there exist good codes. How did he prove it? He said, take a random matrix like M by N matrix, where M, say, is some fraction of N. And then if you just put the bits 0, 1 randomly, and you look at the kernel of this matrix, so you can evaluate the dimension, and he proved easily, that's simple linear algebra, and he proved that with high probability, this is going to be a good code. And after that, people started to have explicit constructions, and there are many explicit constructions that I don't want to talk at this point. I will get to that soon. In the 60s, Gallagher came with another notion which became very important. It took time that people understood the importance of this notion, and this is called LDPC, low density parity check. Now, the code is called low density parity check if it is defined by equations. What does it mean, equation? They are really linear functionals. The coding theory people call it constraints with bounded support. Namely, if you think about this matrix that I mentioned before, which is the linear, which the code is the kernel of this matrix, you really want that every row of that matrix will have only bounded number of non-zero elements. Now, you can understand why this is important for practical purposes, because now you get a vector, you want to check whether there are mistakes or not, then you want to save time. You want that the calculation will be as fast as possible. So you want the matrix to be as sparse as possible. Another way to define LDCP code, and now when I say bounded support again, I mean that the n goes to infinity, but the weight of the rows is bounded independently of n. An equivalent way to say it is look at all vectors in FQ to the n which are orthogonal to the code. Orthogonal in the standard sense, you know, even if it's over a finite field, you know, the inner product or scalar product, I don't know how to call it, between alpha and beta is sigma ai bi. So every such bi define an equation, and those equations define the code. Now in the code C, we don't want to have short vectors, vector with small weight. In C perp, we do want to see there are many. In fact, the code is LDPC, you usually see if and only if C perp is spanned by vectors of bounded weight. Anyway, this was the Gallagher defined it, and he showed by a similar proof to Shannon that random equation, if you take random bounded equation, you take this matrix I described before, but you will make sure when you put randomly the bits that every row will have only bounded number of non-zero bits, still the kernel has a good rate. But unlike the case of code, it took much longer to have explicit construction of LDPC good code. In fact, this was a big breakthrough by Sipser and Spielman in the 90s, who made explicit construction. In fact, when Dan Spielman got the Nevalina Prize some years after that, the committee mentioned that work of him as one of his three great achievements. And actually, mathematically, it's very simple. I will try to give you essentially the full proof for that because we are building on that work. So, the breakthrough was the so-called, what they called expander codes. Expander codes are LDPC good codes. It's not a big problem to get explicit LDCP. It's not a big problem to get explicit good codes, but to make it LDPC and good, this was the challenge. And let me describe the construction of Sipser and Spielman. Sipser, by the way, was the thesis advisor at MIT of Spielman. So let X, so here is the construction. Let X be an R regular graph, so a finite R regular graph. So V is the set of vertices, E is the set of edges, and the degree of every vertex is exactly R. The eigenvalues of the graph, which mean the eigenvalue of the adjacency matrix. The adjacency matrix is, let's say that V is of size M. There are M vertices, so this is an M by M matrix of 0, 1s, just saying whether there is, between any vertices, is there an edge or not. This is a symmetric matrix, so all the eigenvalues are real. And it's not difficult to say that all of them lying between R and minus R. If the largest eigenvalue is always R, if you take this matrix and you multiply it by the vector 1, 1, 1, 1, 1, then you basically count how many ones on every row, so you get R, 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 R. So this is the eigenvalue, and this is the largest eigenvalue. If the graph is connected, this one comes with multiplicity 1, and we are interested in the second largest eigenvalue, which will denote lambda of X. That's very important eigenvalue in much of the theory of expander, random walks on graph. This eigenvalue plays a a role, the crucial role. So let's call here, sometimes people give different definition to expanders, but they are essentially equivalent up to the constant. So I will take the one which is most convenient for me for this talk. So X is called lambda expander for some lambda less than R, if lambda X is less or equal lambda. So again, what we really care, I mean, for one graph is not interesting. We care, we have a family of R regular graphs, the same R for all of them, the number of vertices M going to infinity, and we take a family of R regular graphs such that for all of them, the second largest eigenvalue is bounded above by lambda. In particular, it's bounded away from R. Uniformly for the whole family. This is a family of expander. In a minute, we'll see that we need something more substantial than just expander. We need something which is kind of close to Ramanujan in some sense, to those who are familiar with this topic. But we don't have to. You don't have to. Okay, so what? Okay, let me mention, because we do need we will need it later. The definition: the graph X is called Ramanujan if lambda of X is less than 2 square root R minus 1. And by a famous theorem of Alombo-Pana, this is the optimal you can expect for an infinite family. You won't be able to give a better bound for the second eigenvalue if you take an infinite family of R regular graphs. So these are, in some sense, the optimal expanders, and such explicit construction, I should stress, were constructed in the 80s by Margulis on one end and by Philip, Sarnak, and me. And then we did it when R is equal prime plus 1, as my student Morgenstern later did it for prime power plus 1. So there are, what is important for us with this talk, there are explicit constructions of very good expander, so that the second eigenvalue is much less than the largest eigenvalue. Okay, now let's go back to Sipser and Spielmann. What is their construction? Their construction is the following. Let X be, again, a regular graph, which is also lambda expander. On M vertices, R is fixed, lambda is fixed, and M goes to infinity. Now, they constructed, their idea is very beautiful. They constructed a big code by taking first a small code. What does it mean, a small code? They take C0 to be a fixed subspace of F2 to the R. R is bounded, R is a fixed number. They take a subspace, we'll see they need some properties of this subspace. Now, we label the R edges around every vertex by the letters 1 up to R, and we don't need any consistency, namely the same edge, when it is viewed from one end of it, can get the number 7, and from the other end of it can get the number 13. We don't care. Let's now W, the space, the full space, will be all possible functions from the edges to F2. Now, then, if this is a regular graph on M vertices, so the number of edges is M times R over 2. So the dimension of W is MR over 2, and this number will be N. This is going to be the full space F2 to the N. Now we have to define a subspace of it of dimension K. So let's define the subspace and then we'll evaluate its dimension. The subspace, which we will call the large code, will be all the functions in W such that for every vertex, the local view of F is in the small code. Think about it. you have a function which is defined over all the edges of the graph. When a little vertex is looking around to its neighbors, you see R numbers. So you see a vector in F2 to the R. We want that this vector will be in the small code that we fixed in advance. Okay? So now the theorem of Sipper-Spielmann said the following. If the dimension of C0 is more than half of R, strictly more than half of R, and if the distance of C0 of this little code is more than the lambda of the graph X. So that's kind of an interesting, the first condition A is okay, it's boring. The second condition is the interesting one. Why? Because we relate to two things which on the face of it have nothing to do with each other. The distance of the code is like, what is distance of a code? This is a code in F2 to the R. The distance of it is some number between 0 to R. The lambda of X, you remember, it is also a number between 0 to R, but this is an invariant of the graph, not of the code. That's exactly the point. We want the distance of the graph, of the code, to be strictly bigger than the second largest eigenvalue of the graph. Now, if you have these two conditions, and they show that you can achieve these two conditions by using a Ramanujan graph or even by using random graph, because for R fixed, if you use random, it's fine, because it's not random. You really run an algorithm till you find one, because R is fixed. Anyway, they say C now is LDPC good code. Let me review the proof. The one thing which is sometimes the most difficult in when you look at some codes, this is the simplest thing here, to see that this is LDPC, that the functions defining this code are all bounded, because what are the functions defining this code? You look at the code locally, right? You look at the functions locally. You look at the link of a vertex. You just look at the edges around the vertex, and you have some condition over there. Each one of these conditions is a bounded linear functional, right? It just looks and reads the R less than R bits around that vector. So this is clearly an LDPC code. Why this is a good code in the sense? So let's say what's the dimension. And now the dimension is at least the number of variables minus the number of equations. The number of variables is the number of edges, n. The number of equations is m, which is the number of vertices, times the codimension of C0. To define C0 as a subspace of F2 to the R, you need R minus dim C0. And now it's a two-line calculation to see that this is equal to this number, 2 over R, dimension C0 minus R over 2 times n. Now we assume that the dimension of C0 is strictly bigger than R over 2. So this is a positive number, constant. This is a positive number, constant. So we get that the dimension is at least constant time n. The proof of, okay, so the proof of the distance is slightly more sophisticated, but not really, because what we have to prove? You remember that to prove that that the code is good, is a good distance, you have to prove that every vector, a vector in the code has a large support. So let F be a vector in the code, and capital F the support of it, and let G be the subgraph of X spanned by F. Now they use a lemma due to Noga Alon and Fan Chang, which is very simple. I mean, if I would have another 10 minutes, I probably could give you also the full proof for that one. If you have a subgraph of a graph X, whose average degree L is more than lambda X, then the size of the graph is some constant. You see, this is the constant times the size of x. Now, what happens here? We made a condition which ensures us not just that the average degree is more than lambda x, that every vertex of f has degree more than lambda of x, because if f is non-zero nearby one vertex, because the distance of the small code is more than lambda x, then already around that vertex you will find edges, enough edges more than lambda x, which are not zero. So anyway, this gives you that this code is, the distance is also linear in N, and then you can use either, as I said, either Ramanujan or random to get explicit. Okay, but now I'm starting really my talk in the last 15 minutes, because as Spielmann already wrote in his thesis, what he really wanted to get at the time was not LDPC code, but locally testable code. Now, so let me define what are locally testable codes. A code in F2 to the N, again, you remember when I say a code, I really mean a family of codes when N goes to infinity. It's called Q epsilon locally testable if there exists a random algorithm which for every alpha in F2 to the N, that's the big space, reads only Q random bits of alpha. It reads only bounded number of bits. It answers yes if alpha is in C, and it answers no with probability at proportional to the distance between alpha to C. You take the distance between alpha to C, you normalize it by 1 over n, and there is some constant epsilon. Let me explain. I mean, I think maybe it does not need explain. Oh, it's written here, sorry. Namely, A can decide by reading only few bits of alpha if alpha is in C or far away from C. So let me explain. You are getting now a word of length, a vector of length 200,000. You have an error correcting code that can correct it, but it can correct if the number of mistakes is 5%, 2%, 10%. If 40% of the bits are corrupted, the error correcting code will not be able to correct it. Now, what you want is to read only a bounded number of bits and decide with high probability whether this is a legitimate code word, or maybe you cannot expect to read only 70 bits and say, I will be able to decide with absolute certainty whether you are in the code or not, because if somebody will just flip one bit, it will take you out of the code and you cannot see it if you read only 70 out of 200,000. But you can decide with high probability if that's the goal. If you are at least very close to the code, that the number of mistakes is say not more than 3%. And then you say, okay, then I will apply the error correcting code. It's a massive package. I don't want to apply it. If it's very corrupted, I will ask the sender to send me again. This was the goal. Now, this is beside the practical use. This became a very important problem related to property testing, the so-called PCP in theoretical computer science. I don't want to get to that. First of all, I don't really understand it. And secondly, that will take a long time. Now, there were examples of locally testable code long ago, already in the 80s. For example, here is a locally testable code. Let W be all functions, the space, okay, I'll do it very quickly. The space of all functions from F2 to the M to F2, all functions, not linear functions, all functions. So the dimension of N is 2 to the M here. And the code, the subspace is the linear functions, the linear functionals. So the dimension is M, which is logarithmic in N. And here is a test. You want to check if a function is linear or not. Do the natural test. The natural test will be pick up random x and y and check whether f of x, y is equal f of x plus f of y. So you read only 3 bits of f. And a famous theorem of Bloom, Luby, and Rubinfeld from 93 showed that this is local testability. This is a good test. And I will not go to the precise constant, etc. But the problem with this, that this is not a good code, because the distance of it is fantastic also, but the dimension of it is only logarithmic in n. Later on, there were other LTC code, the Reed-Solomon, the Reed-Muller. I'm not going to talk about them because each one of them, if it was good on one aspect of the code, it was bad on other. Let me just mention one code because I will need it, and this is the Tensor Code. The Tensor Code is a code which defined like that. You take 2 codes. You take C1 in F2 to the N1, and C2 in F2 to the N2. You have to assume that one of them is what they call smooth code. You have to, some technical condition. Let me not bother even to define it. And look at the tensor product of them in the tensor product of the two spaces. You can think of it in a very concrete way by saying that you look at the of the N1 by N2 matrices. So the full space, let's say that N1 is equal to N2. And you can even take that C1 is equal to C2. Then you get n by n matrices. So dimension of the code is n squared. And the dimension of the full space, sorry, is n squared. And then the code words will be all the matrices such that all the rows are in C1 and all the columns are in C2. You can see that the dimension of the code is n1 times n2, so let's say n squared, and the dimension of the code is the dimension of C1 times dimension of C2. So this in principle could be a good code, but it's not LTC in the strict sense, because in order to check it, now what will be the test? The test will be choose random row or random column and check whether you are there. But to check it, you have to read n bits, n out of n squared, which means this is square root bits, and we wanted constant number of bits. So over the years, there were plenty of work on that, that people either improve one aspect of the tree or another. It became, so it was a long-standing problem. Are there good LTC code? Namely, you want code with constant number of queries. That's what they call the, you read only constant number of bits, you read only a Q independent of n, and they are good. So you want constant rate, constant distance, and constant number of queries. So this got the nickname, the C-cube problem: constant rate, constant distance, and constant number of queries. Now let me just say a word. I don't have time to explain more why this is such a difficult problem. Because before that, the paradigm in codec theory was always, or almost always, let's say, I mean, I should be maybe more. We know that codes like what we want exist. Random codes are. Random LDPC code are good. I mean, we know they exist. Here, random codes, even random LDP codes, are not LTC, are not locally testable. That's not so difficult to prove. So this is like we say in Hebrew, we have to look for machat be'arimat shachat, and it's not even clear that the machat exists, or in English, so we have to find a needle in an eye stack. Before that, people look for A in eye stack. Now we have to look for a needle in eye stack. In fact, some of the experts predicted that no such code exists. And there were kind of dispute. There were even conjectures by some of the leaders that you can never achieve it. Anyway, the good news is that we have now explicit construction of LTC good codes. And that's not so difficult. I have only 5 minutes, but I think it should be enough to give basically the construction. It's more complicated to prove than the Spechtman, but it's not so complicated. And what is interesting is that there is a new algebraic construction, combinatorial, that I think should be of interest for group theorists, even independent of coding theory. So let G be a finite group, and let's take two symmetric set of generators for G, A and B. And let's assume that none of them contain the identity, and I want them to be kind of independent of each other in a fairly strong sense. Namely, no element of A is conjugate to no element of B. And I want that the Cayley graph of G with respect to A, as well as the Cayley graph of G with respect to B, will be a good expander. Say even Ramanujan, we don't really need Ramanujan, but really good expander. Now, the new object that we are looking at, which is so surprising why that people have not looked at it before, and maybe somebody in the audience can correct me and give me some reference. You know, usually when we look at a Cayley graph of groups, we say, okay, it doesn't matter if I take the Cayley graph from the right or from the left. Anyway, I'm getting isomorphic graph. It doesn't matter. But why not to take both? Look at it on both sides with respect to two different set of generators. So we define left-right Cayley complex. Now we think of it not as a graph, but as a two-dimensional square complex. Look, we denote it K, A from the left, G and B from the right. We let A act on G from the left and B from the right. Now this gives me a lot of squares. So around every vertex G, I can go by A from the left here. I can go upstairs by B from the right here, and then I can go here and I have squares. So I'm getting a square. Now, this condition of independence was just to ensure that all these four elements are really different than each other. Let's assume now that what we care, what we are going to do, again, we take G goes to infinity, the size of G will go to infinity, and the A of B will be fixed. Let's say that even of the same size, doesn't really matter. We can achieve that. So the number of square is quarter GAB. A is fixed, B is fixed, and quarter is fixed. G goes to infinity. We will take a code in F2 to the A, a smooth code, and in CB, in the function of B, another code, and we look at the tensor code. Now, if you think about it for a second, every vertex, and now we are going to define the code as functions on the squares. You see, we are really building a second floor of a Simter-Spielmann. And this is not just metaphoric saying second floor, it's really second floor in a way, above their code, because we are going to define our codes and our codes are defined on the squares of F2, on the squares of this construction. This will be functions from the square to F2, such that F of every link of a vertex. Now, what links of a vertex sees? A vertex sees around it squares which are in one-to-one correspondence with A cross B. So you can think of it as a matrix A by B. So you can check whether this is inside this tensor code I defined before. Or another way you can say for every edge E of type A, F on the link of A is in CB, and for every edge of type B, F of the link of is in A. And now in the last 1 minute, I will give you the theorem without giving you the technical details, which are not so interesting, to be honest. Under suitable assumption on CA, CB, and R, this is a good LTC code. Now, and it's possible to implement this this assumption. We have codes satisfying and graph and satisfying all what we want. And the test will be just choose a random edge and check only R bits around it, right? You check a bounded number of bits around it because the size of A and the size of B is similar. Now, how do you prove it? So to evaluate, so the fact that this is LDPC is trivial. To evaluate the dimension is linear, is simple linear algebra. To evaluate the distance is like in the Sipter-Spielmann. The new thing, which is more complicated, is to show that the B code is LTC, is locally testable. So we are kind of doing philosophically what Sipter-Spielmann did, propagating the local testability of the tensor code, which is not good for the tensor code itself, because but in our situation, the tensor code is a bounded, is a fixed tensor code. We propagate its local testability to a global local testability of the full code. Now, because the 40 minutes talk, I cannot give you the motivation, and now we got to that. I must mention one name, Garland. Garland already in the 70s proved a conjecture of vanishing of the cohomology of lattices in simple periodic Lie groups. Our work started in very complicated things like Ramanujan complexes, and the periodic uniformization. So we really were working on it for 4 years, and then suddenly it became relatively simple, and the paper should be out in a few days. And it's basically one can teach it in an undergraduate course.
All right. Thank you very much. That was fascinating, really interesting. Are there any questions? I don't hear any questions. So we will get back together in 7 minutes.
Thank you very much.
Thank you again.
אתה אלוף. יפה מאוד.
אלי, דיברת אליי?
כן, כן, יש עוד אלופים פה.
לא שמעתי. What did you say?
It
David,
was
do you want me to
great.
share my screen?
It was great.
Thank you, thank you.
Yeah, excellent.
So Alex, that the condition about the non-conjugacy of the generator, it's sort of a little reminiscent of Beauville surfaces, where you take, two coverings of P1, where the generators of the monodromy group
Right, and
are not conjugate to any one of them.
yeah, but you know that luckily in the previous construction of Ramanujan graphs, but as a Cayley graph, we didn't have to invent something new. Just go back to what I have in my packets, from 30 years ago. But somehow I found it difficult to see a general methodology, because usually the kind of generators we have are generators for some arithmetic group that we pull down to the function and the way. If I take two set of generators which satisfy in the infinite group, which satisfy this condition, let's say that they are not conjugate upstairs, they may well be conjugate downstairs, even for every prime P. That's the example, 3 by 3 matrices which are not conjugate in SL3Z, but conjugate mod P for every prime. It's exactly this local to global.
Right. Yeah, that's right.
That's the principle, which is not true in this case.
Right.
So listen, Bob and Alex, Sue, you're muted. Are you going to try to share your screen?
Sure, yeah, let me try now.
Okay, sorry, Bob and Alex, that was quite interesting, but
No, no, go ahead. Of course, the program should go.
There we are. Okay, good.
Great. Can you see my title?
I see your title and
Great.
it looks like it works great.
Yep. All right, Susan, if you are ready to go, I will introduce you. It's Ready. my pleasure to introduce Susan Sierra, who will tell us about affine Lie algebras and just infinite growth. Susan.
Thank you. Well, I'm very grateful for the invitation to speak. This has been a fabulous conference so far. I've learned a lot about both areas that are close to what I do and also areas that are quite far away. I very much enjoyed it. I also particularly want to thank those of you who have your cameras on, because it's so depressing to give a talk to sort of a screen full of blankness. So thank you very much. So what I'm talking about are some very new results about growth of developing algebras, of affine Lie algebras. And everyone here is, you are an experimental audience, because this is the first time I've talked about these results. So be warned, I suppose. So what's the situation? Well, I'm a ring theorist. So anytime I get a problem in algebra, I try to turn it into a problem in ring theory. So I'm particularly interested right now in infinite dimensional Lie algebras. So when you have a Lie algebra, of course, you turn it into a ring by considering not the Lie algebra, but the universal enveloping algebra of the Lie algebra. Now, for a finite dimensional Lie algebra, these enveloping algebras they're paradigmatic examples of well-behaved, nice non-commutative rings, and they're extremely well studied. And one can argue that basically everything about these enveloping algebras is known or close to known. On the other hand, very little is known about enveloping algebras of infinite dimensional Lie algebras. One of the things that's not known is, is there any sense in which you can consider these enveloping algebras to be well-behaved? I mean, what these enveloping algebras are, right, is they're deformations of polynomials in infinitely many variables, which is a commutative ring with, with all sorts of horrible, uncontrollable properties. And when you start to ask this question, well, what might well-behaved even mean? What is a nice property that you might hope that one of these enveloping algebras of an infinite dimensional Lie algebra might satisfy? So the first nice property that one might want is that this enveloping algebra is left and right Noetherian. The two are symmetric for enveloping algebras. Ken Brown, in one of his survey papers on Hopf-Algebras, says this question is notorious. It's certainly been around for a long time, at least since the Stewart and Amayo book on infinite dimensional Lie algebras from 1974. So is there an infinite dimensional Lie algebra with Noetherian, left and right Noetherian enveloping algebra? I first learned about this question from Lance, who asked with Carolyn Dean in 1990 if the enveloping algebra of the Witt algebra was Noetherian. So here the Witt algebra is the Lie algebra of algebraic vector fields on the punctured complex line. And what it looks like is Laurent polynomials in T multiplied by the operator d by dt, which I'm always going to write as del. So here's the formula for the Lie bracket of f del and g del. One might say this has a good chance of being left and right Noetherian because it's extremely non-commutative. If you just look at the positive part of this Witt algebra, of the Witt algebra, and look at the enveloping algebra, for example, it's so non-commutative that the enveloping algebra surjects onto all Weil algebras of all dimension. So surely, if there's any chance, if there's any Lie algebra, infinite dimensional Lie algebra, where the enveloping algebra is tractable, you want a lot of non-commutativity to control the bad properties of this big polynomial ring. So this was a good candidate to look for Noetherianity. Of course, as I think most people know now, it's not. I proved this with Chelsea Walton back in 2013. And one of the amazing things about the proof of non-Noetherianity for the Witt algebra is actually, in some sense, even though the question was sitting there, as you can see from the dates on this slide, for 23 years. In fact, the proof was also sitting there for basically as long as people have been looking at this algebra. So what's the proof of non-Ethereality? Well, from the construction, there's a ring homomorphism from the enveloping algebra to the localized Weyl algebra. So here I'm writing the localized Weyl algebra, slightly abusing notation, as polynomials in T, T inverse, and del, but we should remember this is a non-commutative ring where del T is T del plus 1. And the map is just, well, I send F times del to F times del. And the fact is that the kernel of this homomorphism, sort of the obvious, the easiest to construct, if you will, ideal, two-sided ideal in the enveloping algebra, this is the counterexample to Noetherianity. It's not finally generated either on the left or on the right. Moreover, from this theorem, you can pretty easily deduce that for any infinite dimensional Z-graded simple Lie algebra of polynomial growth, its enveloping algebra is also neither left or right Noetherian. So specifically, this holds what we've seen for the Witt algebra. Also, if L is a loop algebra, which is an infinite dimensional Lie algebra built out of a finite dimensional simple Lie algebra, and it's Laurent polynomials in T with coefficients in the finite dimensional Lie algebra. And the bracket is the obvious one, xt to the n, yt to the m, bracket to bracket xy, t to the n plus m. And a Cartan algebra, there's a list of these simple Lie algebras, and for all of them, we know that the enveloping algebra is neither left nor right Noetherian. And the proof of the theorem is because there's a list. Olivier Mathieu classified such Lie algebras. The hard one to prove non-Noetherianity of the enveloping algebra is the Witt algebra. And it's an easy lemma that says if you've got a little Lie algebra L1 and a big Lie algebra L2, if the enveloping algebra of the little one is not Noetherian, then neither is the enveloping algebra of the big one. So this gives you a lot of these for free. Just as an illustration of what this lemma gets you, you also get that if you have an infinite dimensional Kac-Moody algebra, then its enveloping algebra is not left or right Noetherian. So why is that? Well, any infinite dimensional Kac-Moody algebra either contains an infinite dimensional abelian subalgebra or a free Lie algebra. The enveloping algebra of an infinite dimensional abelian Lie algebra is just a big polynomial ring in infinitely many variables, not Noetherian. The enveloping algebra of the free Lie algebra is a free algebra, not Noetherian. So therefore, the enveloping algebra of the Kac-Moody can't be Noetherian. So one-sided Noetherianity it's a hard problem. I mean, this question about if there is a one-sided Noetherian enveloping algebra has been open for a long time, and the obvious candidates for an Noetherian, big enveloping algebra, an enveloping algebra, one of these big Lie algebras, don't work. But what about two-sided structures? Let's start thinking about two-sided properties for a definition of well-behaved. And the impetus for thinking about two-sided structures is that the enveloping algebra, the Witt algebra, seems to have very, very few two-sided ideals. So as an illustration of this, remember this homomorphism from the enveloping algebra to the localized Weyl algebra that we used a few slides ago. And remember the property of the kernel of this homomorphism was it was the example for non-Noetherianity, right? It was infinitely generated both on the left and on the right. But as a two-sided ideal, it's actually principal. It's generated by only one element. So you have this gigantic, non-finitely generated two-sided ideal that knocks this huge enveloping algebra down to the size of the Weyl algebra. And in fact, it's principal. So two-sided ideals in this enveloping algebra seem to be very, very big. So because of this, this led me and my collaborator, Alexei Petukov, a few years ago to conjecture that the enveloping algebra, the Witt algebra, actually satisfies the ascending chain condition on two-sided ideals. I can't prove this conjecture, but I'm going to tell you about some suggestive results, which I think at least give moral arguments for why the conjecture might be true. First of all, let's think about growth. The enveloping algebra, the Witt algebra, has infinite GK dimension. I mean, it looks like a polynomial ring in infinitely many variables is the sort of the non-rigorous proof of that. But it turns out that if you take any proper factor of it, then it will have polynomial growth. So I call this the enveloping algebra has just infinite growth or just infinite GK dimension. Let me say a little bit about what I mean here by growth. We've seen it a bunch for groups in this conference, but I think maybe not so much for rings. So of course, I'm taking a finite dimensional subspace and measuring the dimension of its powers. And when I say polynomial growth, I mean the same thing as finite GK dimension. Now, I said the enveloping algebra, the Witt algebra, has infinite GK dimension. One way to see that is if you look at a PBW basis of the enveloping algebra, it's going to correspond to non-decreasing sequences of integers. So it will correspond to generalized partitions. And it's well known that partitions grow very, very fast, faster than any polynomial. So this is remarkable that this is saying that it's not just for this one ideal, the kernel of this map pi, you knock the infinite growth down to finite growth. This happens for any two-sided ideal. And in fact, this theorem can be extended to any central quotient of the enveloping algebra, the Virasoro algebra, which is the unique non-trivial central extension of the Witt algebra. So why is this evidence for this conjecture about sort of two-sided Noetherianity, ACC on two-sided ideals? Well, what this theorem says is that two-sided ideals of the enveloping algebra, the Witt algebra, are huge, right? And therefore, it's sensible to speculate that the ideal lattice might be very, very sparse because ideals are so big, and therefore might be well behaved. Let me give one more bit of evidence for this conjecture on two-sided ideals. And by the way, please feel free to ask questions. I can't tell if there are questions in the chat or not, so you'll have to ask them out loud. So this theorem is a theorem of myself and Omar Leon Sanchez from last summer. And it goes back to Mathieu's classification of, question? No, I don't think so. It goes back to Mathieu's classification of Z-graded simple polynomial growth Lie algebras. If you have such a Lie algebra, then its symmetric algebra satisfies the ascending chain condition on radical Poisson ideals. So remember, the symmetric algebra is just a polynomial ring where the variables are a basis of your Lie algebra, but it has this additional Poisson structure induced from the Lie bracket. So that is, it's a Lie algebra as well with this curly braces Lie bracket. And a Poisson ideal, the symmetric algebra is an ideal as a ring, which is also a Lie ideal for the Poisson bracket. Why is this theorem evidence for this conjecture about two-sided Noetherianity? Well, the symmetric algebra is the associated graded ring of the enveloping algebra under the obvious length filtration. And by standard techniques, if we had ACC not on radical Poisson ideals, but on all Poisson ideals, right, then I would get ACC on two-sided ideals of the enveloping algebra. Now, we don't have ACC, or we don't know whether or not we have ACC on all Poisson ideals, but at least this is saying something about the lattice of Poisson ideals of the symmetric algebra being, I guess, well behaved in some sense. So again, I think this provides some sort of moral argument for why the conjecture of ACC on ideals in the enveloping algebra might be true. So, as I said, so we've got moral support from these two different theorems for two-sided Noetherianity for the Witt algebra. But the second theorem holds more generally than just for the Witt algebra. It holds for all of these Lie algebras that simple and polynomial growth and graded. So this immediately suggests trying to extend the theorem about just infinite growth from the Witt algebra to more algebras on this list. And so this is most of what I want to talk about today, is a very new result that says that enveloping algebras of loop algebras also has to have just infinite GK dimension. This is joint work with Reka Biswal, who is a postdoc at Edinburgh, working with me. And I should say also, everything from here on is very new. It's still being written up. So it has what Toby Stafford would call health warnings, or what I think was referred to in Monday's talk. All these theorems should be in inverted commas. So I want to talk first a little bit about the proof, and in particular to say why this is a more difficult theorem than the theorem for the Witt algebra. So to do that, I need to go back to talking about the Witt algebra. The key lemma that we use to prove just infinite for the Witt algebra is the following result. So this is, well, it's from the paper with Natalia Ayudu, who was also mentioned in Agata's talk, but I'm giving due credit to my co-author here. And I've put her name in larger font than mine in this lemma, because really this lemma is really largely due to my co-author and not to me. So the lemma is a little bit technical, so I'm going to slow down and try to explain it clearly. The Witt algebra is Z-graded, right? And what's the grading? Well, you give T degree 1 and del degree -1. It's the standard grading you'd put on the Weil algebra. And in terms of this grading, the homogeneous basis is therefore a power of T times del. So let's call these elements E sub I. And let's let W plus be the span of all of these guys with positive powers of T. And let me take an element F in the enveloping algebra of W plus, a non-zero element. Let's let J be the two-sided ideal generated by F. And I'll need two numbers. I'll need the length of F. This is the how many elements from the Lie algebra show up in the component monomials of F. And I'm going to need the biggest letter that occurs in F under the obvious ordering on the generators of the Witt algebra. So the lemma is that all monomials in the EI that have at least K letters that are bigger than E2N can be rewritten modulo J as a linear combination of smaller monomials. So implicit in here, there's the ordering on monomials, not just on a basis of the Lie algebra, which I'm not going to define. How do we prove this lemma? Well, we have this element F of length K. We want to be able to rewrite other words, other monomials of length K. So we need to, from this element F, get other elements in the ideal J of the same length. The way you do that is applying commutators. Right? And the key is to prove this lemma is to be able to find a formula for a bracket, a commutator of K different generators against this element F, and to predict what the leading term of that is going to be in this monomial ordering. On the one hand, this involves some tricky combinatorics, some tricky and delicate combinatorics. But on the other hand, you are really helped by the fact that almost all of the Lie brackets in W are non-zero. In fact, the only time you get a zero bracket in W is when you try to take X bracketed with itself, right? So anytime I do a commutator in the Lie algebra, or indeed in the enveloping algebra, I expect to be able to understand and predict what I should get out the far side. I expect to be able to get a nice formula. So why does this help? Why does this reduction lemma help with this growth result? Well, here's the lemma, right? It says that all monomials that have k or more big letters bigger than 2n, can be rewritten modulo j in terms of smaller monomials. So what this says is that the quotient u of w plus mod j can be spanned, therefore, by monomials that have fewer than k big letters, right? So a monomial that has fewer than k big letters, right, looks like m1 times m2, where m1 involves only small letters that can be any length, but only involves finitely many letters, and m2 can involve letters that get as big as you want, but involves no more than k of them. So it's an exercise in combinatorics that the number of monomials that look like this, or if you like, the number of m1s and the number of m2s of a given degree, grows polynomially. And this tells you that u of w plus mod j has polynomial growth. And then one has to extend this argument to work not just for factors of u of w plus, but also for factors of u of w, but one can do this. So I started to talk about this proof because I had presented this theorem for just infinite growth for enveloping algebras of loop algebras. So let's now go back to the loop algebra setting. So we have a version of this lemma for loop algebras. So what does it look like? Well, I start with a basis of my underlying finite dimensional Lie algebra. Instead of thinking of W plus, I'm now going to think about the current algebra of G. I'll write this L plus. So this is not Laurent polynomials in T, but just standard polynomials in T with coefficients in little g. Again, I'm going to take a non-zero element in the enveloping algebra, look at the two-sided ideal generated by it. And just to, when I first started working with these Lie algebras, it was a little difficult to get my head around what elements in the enveloping algebra looked like, sort of because the notation was confusing. So what my element F looks like, right, is, well, it starts with a monomial that looks like some coefficient, and then a basis element times a power of t, another basis element times another power of t, maybe k of those, right? Again, I'm going to want k to be the length of F. And let's say the largest power of t occurring in F is n. So then any monomial in sort of, they're called letters, right? Because elements of the enveloping algebra are spanned by words in a basis for the Lie algebra, and the basis for the Lie algebra now looks like some little g times some power of t. So g sub I t to j, I'll call it a letter. And if I have a monomial in these letters that has k or more powers of t that are bigger than 2n, then again, just as in the statement of the lemma for the Witt algebra, I can rewrite it modulo j as a linear combination of smaller monomials. And again, it's an exercise in combinatorics that this gives polynomial growth for u of L plus mod j, and extending it, you get polynomial growth for proper factors of the enveloping algebra of the full loop algebra. But this lemma is more difficult than the lemma for the Witt algebra. And the reason it's more difficult is because L plus is sort of much more abelian than W, right? I mean, the key technique for the lemma for the Witt algebra was that we had a formula that could predict the leading term of some element we obtained from F via commutators. But now lots of Lie brackets are going to be 0, So you have to be careful about which elements you commute with F, and you still want to be able to control the leading term. And this turned out to be surprisingly tricky, but we were able to do it. So I want to give a few applications of this result. The first, I'm not sure is that significant, but I just think it's cute. So we have our loop algebra. We have the underlying finite dimensional simple Lie algebra. We have an ideal in the enveloping algebra of the loop algebra with this underlying simple Lie algebra. Take an element X in the underlying finite dimensional Lie algebra. Then this ideal contains an element which involves only the element X from the finite dimensional Lie algebra and involves only prime powers of T. So going back to the previous slide, right, this is what an element F in the enveloping algebra looks like. There's some elements from the finite dimensional Lie algebra, there's some powers of T, and what I'm saying is that all the GIs are equal to X, and all the J's here are prime. And there's nothing special about primes. I could pick my favorite infinite subset of Z. I could say that all T powers are powers of a Google, for example. And again, I'd have an element that looked like that in my ideal J. So what's the proof? Well, let's look at the span of all the elements that look like X times T to some prime power. Because the only element I'm using from the underlying Lie algebra is X, this is an abelian Lie subalgebra of the loop algebra. So the enveloping algebra of this A, well, it's polynomials in infinitely many variables. That has infinite GK dimension. But we know that when I factor out J, I get finite GK dimension. I see there's a misplaced right parenthesis there, but you can figure out what that's supposed to say. So there's no way that the map from the enveloping algebra of this A to this factor of the enveloping algebra loop algebra can be injective. So as I said, I don't know the significance of this result, but I also don't know a way of proving it without using growth, without knowing that the growth of the enveloping algebra of the loop algebra is just infinite. So here's well, first of all, let me extend the result for loop algebras to affine Kac-Moody algebras, which was the title of my talk. So let's take an affine Kac-Moody algebra, let's call it L. Let's call the center of this Lie algebra, let's call it C, and let's pick a scalar lambda. Then U of L factored by C minus lambda, again, has just infinite growth. So let me remind you what these affine Kac-Moody algebras look like. As a vector space, it looks like a loop algebra together with this element C, this central one, and with another element D. And what's the Lie bracket? Well, when I bracket together two things from the loop algebra, I get the loop algebra bracket. And then if n plus m is 0, I get some multiple of the central element C. Here, this K here is just the killing form on the underlying finite dimensional one, the invariant bilinear form. And C is central, as I said, and D acts like the Euler operator. It just measures the degree of elements. So when I take a central quotient of the enveloping algebra of this Kac-Moody, this affine Kac-Moody, what I get is something that's a deformation of an aura extension of the enveloping algebra of the loop algebra by this degree measuring derivation D, by this Euler operator. So I hope it's believable that since the enveloping algebra of the loop algebra has just infinite growth, so does this deformation of the aura extension. And I'm not going to say more about the proof of that. So I gave a sort of a trivial application of this just infinite growth theorem. Now I want to give a non-trivial application and compute the annihilators of some very interesting representations. So let's take our affine Kac-Moody algebra And then we can compute the annihilator of any irreducible integral highest weight representation of this Lie algebra. So these, just like with finite dimensional Lie algebras, these are indexed by weights in now the affine root lattice. And any such representation in particular, because it's irreducible, it has what's called the level, that is the center C acts by some scalar lambda. So the theorem is that the annihilator of this highest weight representation is precisely generated by C minus lambda. As far as I know, none of these annihilators had been computed before, except in the situation where V was actually a Verma module, which is a famous paper of Chari's from 1985. So what's the proof of this annihilator computation? Well, the annihilator certainly contains C minus lambda. Right? We said that the center acted by lambda. I'm going to do here what I do for my undergraduate lectures. Right? If I'm doing a proof by contradiction, I'll sometimes circle the statement that I'm going to try to prove is false in red chalk. So here I am circling it in red. Suppose the annihilator is strictly bigger than C minus lambda. Well, we know that the enveloping algebra has just infinite growth. Sorry, the enveloping algebra mod C minus lambda has just infinite growth. So if I factor out an ideal that's bigger than C minus lambda, then I get something that has polynomial growth. So then my representation V, well, of course, it's really a module not over the enveloping algebra, but over the enveloping algebra modulo the annihilator. So it must also have polynomial growth. On the other hand, all these V's are extremely well studied. And in particular, the Hilbert series, which usually gets called the Q character in the representation theory world, the Hilbert series are known. And all of these representations have strictly sub-exponential growth, by which I mean they grow faster than any polynomial. So these can't both be true. It can't have polynomial growth and also grow faster than a polynomial. So therefore, the annihilator has to actually be equal on the nose to C minus lambda. Let me give an example here of what these Hilbert series look like. So let's do the Lie algebra is going to be affine SL2. The level is going to be 1. Then the Hilbert series, which is just the generating function for the size of the graded pieces of my representation. So the dimension of Vn times q to the n. It's an infinite product, the product of 1 over 1 minus q to the 2j minus 1. And when you expand this out and figure out what the dimension of Vn is, you find the dimension of Vn is a number of ways of writing n as an odd partition, writing n as a sum of odd numbers. The number of odd partitions of n is the 9th integer sequence in the encyclopedia. And it grows like e to the root n times some polynomial, which I think alpha here is negative. So e to the root n divided by some polynomial. But in any case, it grows faster than any polynomial. So I said that the Hilbert series of these representations is known, and you can show from this known Hilbert series that they all have faster than polynomial growth. But in fact, the formula for the Hilbert series of V is, I believe it's due to Katz. And there's a known formula for the Hilbert series, which in general is a complicated infinite product that looks a bit like this, only much worse, much harder to get your hands on. So what we do is we actually reduce to the SL2 case, the affine SL2 case, and prove sub-exponential growth just by looking at the Hilbert series of representations of affine SL2. So in my last few minutes, let me just say briefly what's going to happen next. Well, there's lots and lots of open questions. One of the things that really seems to be true is that even though these are very, very big algebras, They're much more tractable than I initially had expected them to be when I started working. I mean, you can say in some sense my trajectory in working on these enveloping algebras has been, well, I started out by proving that most of them, lots and lots of them are non-Noetherian and really badly behaved. And now what I'm actually doing is trying to prove that they're well behaved. And I think it's probably true that both of these are true as long as we find the correct definition of what well behaved means for these enveloping algebras. So what is the class of Lie algebras that have this just infinite growth property? Clearly, not all infinite dimensional Lie algebras have this, right? If you have a free Lie algebra, this fails. If you have an infinite dimensional affine Lie algebra, it fails. But it seems to happen a lot more often than one might expect. I mean, frankly, it surprised me that it happened at all for the Witt algebra. And also this question about ACC on two-sided ideals, which I still think is really interesting. You know, do any of these infinite dimensional Lie algebras satisfy this? This, of course, this question, as I've asked here, is of course very hard. It contains the question for the Witt algebra, which I said earlier in the talk I couldn't answer. So maybe isn't precisely fair to put as a question, but it's certainly something that I'm thinking about. All right. So let me wrap up by making three final comments. The first is sort of silly. It's actually surprisingly, when I was very struck, you know, in working on this, I needed to look up what was the asymptotic behavior of these odd partitions. So of course I went to the encyclopedia and looked it up. And then I was like, wow, this is only the 9th integer sequence. I wonder what the first and second and so forth integer sequences are like. I had this conjecture that the ordering is somehow by significance, and you know, then it was the 9th most important integer sequence. I'm not sure that's true, although I suppose that certainly for an algebraist, one might want to argue that that A1 is in fact the most important integer sequence. It contains the information of all the primes, right? So the number theorists can't be annoyed at me here. Secondly, an announcement, which is just there's a couple of jobs available at Edinburgh. So if you know anyone who's looking for jobs, let them know. And thirdly, thank you very much for inviting me to speak.
Well, Sue, thank you very much. Any questions?
Yeah, I have a question. So back to symmetric Poisson algebras. So you proved that for simple algebras of finite growth, you have ACC on Poisson radical ideals. So I wonder if you have anything further to say on the structure of the Poisson prime spectrum. I guess it's too much to hope for finite Poisson cool dimension, but maybe you can say anything else.
Yeah, sorry, I'm looking for the slide about Poisson ideals, and I managed to go right by it. Yeah. So actually, I can say quite a lot about Poisson ideals. For starters, for both the Witt algebra and for loop algebras, there are Poisson versions of these theorems that they have just infinite growth. So for the Witt algebra, if I look at the symmetric algebra and factor out any non-trivial Poisson ideal, again, I get polynomial growth. And similarly for loop algebras and for affine algebras. And then looking at the structure of Poisson ideals is very interesting. That's actually a different talk, but I have a paper out with Petukov this past summer about Poisson ideals for the Witt algebra. I think rather than say anything more about that, I'll just refer you there.
Any other questions?
I enjoyed the talk. And is it any literature and reference? Can you provide some reference?
So all of this is very new. It's still being written up, but we intend to have a paper on the archive certainly by the end of 2021. So which is not that far away.
Okay, I would be happy to read.
Anyone else? Well, thank you again, Sue, and the next talk is in 10 minutes. All right. It is my pleasure to introduce Igor Rapinchuk, who will tell us about algebraic groups with good reduction and the genus problem.
Okay, thank you, David, for the introduction. Thank you very much to the organizers for the opportunity to give a talk in this conference. It certainly would have been nice to see everyone in Israel, but given what things are, it's wonderful to be able to participate in this event virtually. So as my title indicates, I'll be talking about algebraic groups with good reduction and some connections to the genus problem. Okay, so before really getting started on the talk, let me sort of explain what I mean here. So in the past, my co-authors and I have spoken quite extensively about the genus problem. And in some sense, today's talk can be seen as a continuation of the previous talks. So more precisely, what I mean is that, well, initially the focus of the genus problem was on studying division algebras having the same maximal subfields. And there's still certainly plenty of unresolved questions there. But another direction, which has gained some traction over the past few years, has been the genus problem for algebraic groups, which is concerned with the analysis of algebraic groups having the same maximal tori over the field of definition. And well, what is perhaps somewhat surprising, at least initially, is that this genus problem, as well as several other problems, turn out to be quite closely connected to the analysis of groups with good reduction. So that, broadly speaking, is the story that I would like to sketch today. Okay, well, so to establish the appropriate context for what will come a little later in the talk, I would like to begin by recalling some of the key points concerning the genus problem for division algebras. Okay, so the starting point is the following question. Suppose we have two finite dimensional central division algebras over a field K. What can we say about these algebras if they have the same maximal subfields? And precisely what this means is that, first of all, the two algebras have the same degree, say n. And secondly, a degree n field extension P of K embeds into one algebra if and only if it embeds into the other. Okay, well, in the case that we ask a similar question, but the division algebras have the same splitting fields, this problem is addressed by the famous theorem of Amyosur, right, which says that, well, if we have two division algebras, D1 and D2 over a field K, and we assume that they all have the same splitting fields, then it turns out that the Brouwer classes of these division algebras generate the same subgroup of the Brouwer group of K. And one of the key points of the argument is that it relies on certain infinite dimensional splitting fields called generic splitting fields. So, well, a natural question to ask is it possible to prove a similar result, but restricting our attention only to finite dimensional splitting fields, or even just maximal subfields? And well, the answer turns out to be no, already for cubic division algebras over global fields. So just to briefly illustrate this point, and as I said, I'm not going to go into too much detail regarding this, but just to illustrate things, let's stick to the case of the rational numbers. Then we have the well-known exact sequence given to us by the Artin-Hasse-Brauer-Noether theorem, which basically says that any division algebra over Q is determined by its local invariance. And then by suitably choosing these local invariants, it's possible to construct arbitrarily large, but still finite families of non-isomorphic cubic division algebras, all of which have the same maximal subfields. On the other hand, any such algebra, of course, generates a cyclic group of order 3 in the Brouwer group. So there are just two generators. So what we see is that there are plenty of division algebras which have the same maximal subfields, but they generate different subgroups of the Brouwer group. So in other words, what this shows is that Amitsur really found the correct approach to this problem of studying algebras having the same splitting fields by considering these generic splitting. Now, in order to formalize this discussion regarding division algebras having the same maximal subfields, it's convenient to introduce the notion of the genus of a division algebra, which was initially suggested by Louis Rowan. So suppose that we have a finite dimensional central division algebra over a field K. Then we define the genus of this algebra to be the collection of Brouwer classes that are represented by division algebras having the same maximal subfields as our algebra. And then once we have this definition, there are several natural questions to ask. So let me mention just two. First, when is the genus trivial? That is to say, when does it reduce to a single element? So notice that this is simply another way of asking when the algebra is determined up to isomorphism by its maximal subfields. And more generally, we can ask, when is the genus finite? Well, over number fields, it probably doesn't come as any surprise that we can completely resolve these questions by using the Albert-Brouwer-Hasse-Noether theorem. So on the previous slide, I stated the theorem for Q, but in fact, basically the same theorem holds for any number field. And what we see there is that, well, first of all, any quaternion division algebra has trivial genus. And generally speaking, the genus is finite for any division algebra of arbitrary degree. Okay, so the situation is completely understood for number fields, but what about more general fields? Well, I would like to mention two results. The first is what we like to refer to as the stability theorem. So basically what it says is if we have a field little k with a property that any quaternion division algebra over little k has trivial genus, then this property also carries over to quaternion division algebras over the field of rational functions over little k. Okay. Now, so here we don't really make any assumptions on our field, but I should say that historically, the first case of this problem concerned division algebras over Q of x. And this was settled by Skip Garibaldi and David Salton. In fact, they considered some more general situations, but that's, in particular, they established the stability for Q of x. And another thing that I should mention is that although I formulated the result just for quaternion algebras, there's an analogous statement for algebras having exponent. Okay, so so this is concerning the triviality of the genus. Now, one thing to note is that if our algebra does not have exponent 2, then its genus is necessarily non-trivial because at the very least, the genus will contain both the algebra and the opposite algebra. So the only thing that we can really ask for algebras that are not of exponent 2 is whether or not the genus is finite. And the point is that over arbitrary fields, the genus may very well be infinite. So there's a construction which was suggested by a number of people, and was sort of organized systematically by Jeff Meyer, who showed that over certain very large, so infinitely generated fields, it's possible to construct quaternion algebras with infinite genus. And then a little later, this construction was also extended to algebras of arbitrary prime degree by Sergei Tikhonov. Okay, so the point is that if we do not make any assumptions on our field, then it's very possible that the genus could be infinite. And well, the thing to point out is that in these constructions, the fields are very large. So in particular, they're infinitely generated. On the other hand, it turns out that the genus is far better behaved over finitely generated fields. So what we show is that if K is a finitely generated field, and by this I mean that it's a finitely generated extension of its prime subfield, then the genus of any division algebra D over K is finite. And the proofs of both the stability theorem and the finiteness theorem make extensive use of the analysis of ramification of division algebras and central simple algebras. And in particular, they rely on information on the so-called unramified Brauer. Okay, so I won't go into the details regarding this, but let me just briefly mention the key definitions. Well, so first of all, there are several equivalent ways of talking about ramification for division algebras and more generally for central simple algebras. So let me mention just one approach, which is sort of closest in spirit to what will come a little later in the talk. Okay, so suppose that we have a field K that is equipped with a discrete valuation V. So then we say that central simple algebra A over K is unramified at V if, well, it essentially arises from an Azumaya algebra over the valuation ring of the completion. So that is to say, we have this Azumaya algebra script A over OV, and when we base change up to KV, that this is the same as the base change of A up to this completion. Okay, and furthermore, if our field K happens to be equipped with a set V of discrete valuations, we can consider the associated unramified Brauer group, which by definition consists of the Brauer classes that are unramified at all places V and V. Okay, so those are the two key definitions regarding ramification. And now let me formulate the key fact that's really at the heart of the proofs of both the stability theorem and the finiteness theorem. So again, suppose that we have a field K equipped with a discrete valuation V, and moreover, let's fix an integer n that's relatively prime to the characteristic of the corresponding residue field. Now, if we have two division algebras D1 and D2 of degree n, which have the same maximal subfields, then one can show that both algebras are either simultaneously ramified or unramified. And using this fact, the proof of the finiteness theorem essentially reduces to establishing a finiteness result for the unramified Brauer group. So specifically, we show that if K is a finitely generated field and V is a divisorial set of places of K, and I will talk about these divisorial sets a little in more detail a little later in the talk. But anyway, suppose we have such a set V, then we show that the n torsion of the corresponding unramified Brauer group is finite for any integer n, which is relatively prime to the characteristic of K. Okay, so that's just a very quick recap of the genus problem for division algebras. So now let me go on to talking about the corresponding problem for algebraic groups. And well, to begin with, probably the most natural way of extending this problem from division algebras to algebraic groups is basically to replace maximal subfields by maximal tori over the field of definition. Okay, so let me make this more precise. So suppose we have two semi-simple algebraic groups, G1 and G2, both defined over field K. So then we say that our groups have the same isomorphism classes of maximal K tori if every maximal K torus T1 of G1 is K isomorphic to a maximal K torus T2 of G2 and vice versa. Okay, so that's what we mean by groups having the same maximal tori. And then how do we define the genus? Well, given an absolutely almost simple algebraic group, G over K, we define its genus, or if we need to specify the field, it's K genus, to be the set of isomorphism classes of K forms, G prime of G, which have the same maximal K tori as G. Okay, so as I said, basically, we take the definition of the genus of a division algebra, and we sort of replace maximal subfields by maximal tori. Well, I mean, now that we have this definition, we can ask analogous questions to what we consider in the case of division algebras. So first, when is the genus trivial? That is to say, when does it reduce to a single element? And also we can ask, when is the genus finite? Well, in the case of number fields, both of these questions were completely resolved by Gopal Prasad and Igor Rapinchuk in connection with their work of weakly commensurable subgroups of algebraic groups. And what they showed is that if G is an absolutely almost simple, simply connected algebraic group over a number field K, then first of all, the genus is always finite. And in fact, in a lot of cases, it's actually trivial. So specifically, if G is not of type AN, D to n plus 1 or E6, then the genus is actually trivial. Okay, so for number fields, the problem is completely settled. Now, on the basis of this result, and quite a number of others, which I'll mention towards the end of the talk, let me formulate a conjecture about what we expect to happen with the genus over more general fields. Okay, so first we have a conjecture as to when we expect the genus to be trivial. So here we take capital K to be the field of rational functions in one variable over a number field, and G an absolutely almost simple, simply connected group whose center has a size at most 2. Then, in this case, we expect the genus to be trivial. And in general, if we have an absolutely almost simple group G over an arbitrary finitely generated field, then we expect the genus to be finite under, some minor restrictions on the characteristic of K. So specifically, the characteristic should not divide the order of the Weil group. Okay. Now, as I said, in the case of division algebras, the analysis there was heavily based on the ramification properties of division algebras. And what has turned out to be quite a fruitful approach in this context is basically to try to do something similar with algebraic groups. But now, rather than looking at unramified division algebras, we have to focus our attention on groups with good reduction. Okay, so in this next subsection, I would like to recall some of the key definitions pertaining to groups with good reduction, give some examples, and formulate our main fineness conjecture. And then I will indicate the precise connection between groups with good reduction and the genus problem. Okay, so let me start right away with the definition. So suppose we have a field K that is equipped with a discrete valuation V. So then we say that a reductive algebraic group G defined over K has good reduction at V if there exists a reductive group scheme, script G, over the valuation ring of the completion, whose generic fiber is isomorphic to the base change of G up to the completion. And then an automatic consequence of the definition is that the special fiber, or the reduction of G, is a connected reductive group over the residue field of the same type as our original group G. Okay, so this is, of course, a slightly technical definition, but so intuitively speaking, the key point here is that, the property of good reduction basically means that our group has a nice integral structure over the valuation ring, and moreover, this structure behaves well under reduction. Okay, so that's really sort of the point of good reduction. Now, although the precise definition is somewhat technical, it turns out that in a number of cases of interest, it's possible to talk about good reduction in fairly concrete terms. Okay, so let me just mention a couple of examples that are good to keep in mind. Well, so first of all, if our group happens to be split over K, then it actually has good reduction in any place V. And the reason is that, according to the Chevalier construction, any such group actually arises from a group scheme over C. Okay, another example where it's possible to describe the condition of good reduction fairly concretely is for the groups SL1A, where A is a central simple algebra over K. So remember, recall that these are the groups associated to elements having a reduced norm 1 in the algebra. So then it turns out that such groups have good reduction at a place V, if and only if the algebra is unramified at V in the sense that I defined earlier in the talk. That is to say, the algebra arises from an azimuth algebra over the valuation. And another example, which will be relevant for us a little later when I talk about available results, is a good reduction for spinor groups of quadratic forms. So it turns out that such a group has good reduction at V if up to scalars our form is equivalent to a quadratic form, all of whose coefficients are units at V. Okay, so these are just some examples. Now, before I formulate the general problem that we're interested in studying concerning groups with good reduction, let me just quickly recall another definition, which actually I already briefly used this term earlier in the talk. So that's the notion of the K-form of an algebraic group. So recall that if we have an algebraic group G over K, then a K-form is an algebraic group G prime, which becomes isomorphic to our group G over a separable closure of K. So for instance, if we take a central simple algebra of degree n over K, then it's well known that over K bar, it's really just a matrix algebra. And so therefore, the corresponding group SL1A is just a K-form of SL. Okay, so now that we have the notion of good reduction, and also I recall the notion of a K-form, so here's the general problem that we would like to address. So suppose we have a field K, which is equipped with a set V of discrete valuations, and we have a reductive algebraic group G defined over K. So then we would like to understand the K-forms of G that have good reduction at all V in V. Now, of course, stated at this level of generality, I mean, this question is basically hopeless. So in order to make the problem really meaningful, we really should specialize, the field K, the set V, and possibly also the group G. Now, most previous work has dealt with what I like to refer to as the Dedekind case. So namely, there one takes the field K to be the fraction field of the Dedekind ring R, and then V is the set of discrete valuations of K associated with the maximal ideals of R. So, well, as far as I know, this situation was studied systematically first in the work of Harder, and then a little later by Kaliotelen and Sansuk. Now, the arithmetic situation, that is to say where R is the ring of integers, so this was studied in detail by de Grosse in the 1990s. And then there was also some follow-up work on this topic by Brian Conrad more recently. The geometric case of this problem, that is to say where R is the ring of polynomials in one variable over little k, was studied by Raghunathan and Ramanathan in their work on torsors over the affine line. And more recently, the corresponding problem was also studied by Chernosov, Agili, and Pianzola in their work on torsors over the punctured affine line. So that's where the ring is the ring of Laurent polynomials. Okay, so basically the Dedekind case is reasonably well understood in a lot of situations. Now, what our work has done is it has really, made some of the first steps in analyzing this problem in a higher dimensional setting. Okay, so more specifically, here's the situation that we study. So we take K to be an arbitrary finely generated field. And then to define our, so-called divisorial sets of valuations, we need to consider a model of our field, that is to say a normal integral affine scheme whose function field is K. And then we work with the corresponding divisorial sets. So these are the discrete valuations of K, which are associated with the prime divisors on our model. So that's sort of the geometric setup. This situation can also be described in purely algebraic terms. So namely, finding a model basically amounts to finding a subring R of K, whose fraction field is K. So this ring should be a finely generated algebra over Z or Fp, and it's integrally closed in K. And then the set V corresponds just to the height 1 prime ideals. Okay, so this is the situation that we study. And what is our main fineness conjecture? Well, we take K to be a finely generated field equipped with a divisorial set of places. And we take G to be a reductive algebraic group over K. So then we expect that if the characteristic of the field is good, in a sense that I'll specify in just a second, then the set of isomorphism classes of K forms G prime of G, which have good reduction at all V and V. So we expect this set to be.
May I ask a question, please?
Absolutely, yeah.
Don't you require smoothness in the model?
Well, yeah, I mean, we certainly can require smoothness, but just for defining the divisorial set, so it's sufficient to require it to be normal. But sure, we can take a smooth model.
Thanks.
Okay, so basically we expect the set of isomorphism class which have good reduction of K forms which have good reduction to be finite. And what do we mean by good characteristic? Well, so for absolutely almost simple groups, we take characteristic to be good if it's either 0 or does not divide the order of the Weyl group. And for tori, we take only characteristic 0. Okay, so that's our conjecture. So why do we refer to it as our main fineness conjecture? Well, it turns out that this conjecture is closely related not only to the genus problem, as I will indicate in just a second, but also to a number of other problems concerning the arithmetic of algebraic groups over arbitrary finely generated fields. Okay, so what is the connection to the genus problem? Well, so recall that in the case of division algebras, the key observation was that if we have division algebras that have the same maximal subfields, then they're either simultaneously ramified or unramified at a place V. So for algebraic groups, we have the following partial analog. So suppose that G is an absolutely almost simply connected algebraic group over K, and K happens to be equipped with a discrete valuation V. And moreover, assume that the residue field is finely generated and our group has good reduction at V. Then what we show is that every G prime in the genus of G also has good reduction at V. And moreover, the reduction of G prime lies in the genus of the reduction of G. So informally speaking, this property of having good reduction basically propagates from G to all G prime in the genus of G. Okay, so now, so this is the key statement. And as a corollary, if we have a finely generated field K equipped with a divisorial set V, and G is an absolutely almost simply connected algebraic group over K, then we can find a finite subset S of V, which in general will depend on the group G, such that all G prime in the genus of G have good reduction at all places V outside of S. So concretely, what this means is that if we know our main conjecture for all divisorial sets, then as a consequence, we obtain the finiteness of the genus. So in more conceptual terms, what this means is that our main fineness conjecture provides a uniform approach to the genus problem for algebraic groups. Okay, so this is the key connection that I would like to mention in this talk. But as I said, the main conjecture has close connections to a number of other problems. So for instance, it's related to the study of local global principles for algebraic groups over finely generated fields. And moreover, I mean, the conjecture, the proof of the conjecture itself in several situations is closely connected to fineness properties of unramified cohomology. And another place where the main conjecture comes up quite naturally is the analysis of weakly commensurable Zariski-dense subgroups of algebraic groups and applications to some classical problems on locally symmetric spaces. So this is work which was initially carried out by Gopal Prasad and Igor Rapinchuk. Okay, so I mean, so basically from a conceptual point of view, the point of studying groups with good reduction is that this idea occupies a central place in the emerging arithmetic theory of algebraic groups over higher dimensional fields. Okay, and so I'm nearly out of time. So in the last few minutes, let me just briefly mention a few fineness results that we have obtained. So first, I should say that the main conjecture has been completely settled for algebraic tori. So what we show is, so let me first mention the resulting characteristic 0, and then I'll say what is known as in positive characteristics. So in characteristic 0, we show that if K is a finely generated field equipped with a divisorial set of places, Then for any D, the set of K-isomorphism classes of D-dimensional K tori, which have good reduction at all V and V, is fine. So that's in characteristic 0. In characteristic P, so we need to impose sort of the obvious restriction. So that is to say, we need to restrict our attention to tori for which the degree of the minimal splitting field is prime to P. And that's certainly a necessary restriction, as I mean, we can work with Artin-Schreier extensions in characteristic P. So if we don't impose this, this condition, there is no hope for fineness. Okay, so the main conjecture is completely settled for algebraic tori. Now, let me mention a couple of results for inner forms of type A. So recall that these are groups of the form SL1A or SLND. So here we use, in a crucial way, our fineness results for the unramified Brauer group, as well as our fineness results for the genus. So regarding good reduction, what we show is that if K is a finely generated field equipped with a divisorial set V, then under some natural characteristic assumptions, the number of isomorphism classes of groups of the form SL1A, which have good reduction at all V and V. So this set is finite. So this basically establishes the main fineness conjecture for such groups. And regarding the genus, we have two results. First, concerning the triviality of the genus. So here we take our fields to be the field of rational functions over either a number field or a finite field. So then for the groups SLMD, the genus is finite. And in general, for groups over finely generated fields, the genus is finite. Okay, and so let me not go into detail regarding the other results because I'm essentially out of time. But another class of fields which we have investigated in quite a lot of detail are so-called two-dimensional global fields. So these are either function fields of curves over number fields or function fields of surfaces over finite fields. And there we have finiteness results concerning good reduction for spinor groups, as well as groups of certain special unitary groups of type A and Cn and groups of type G2. And then we have corresponding finiteness and triviality results for the genus. Okay, and just to finish up, I should say that all of what I talked about, as well as some of the history of groups with good reduction, as well as background, a number of conjectures and available results. So all of this is described in detail in this survey, item 7, and sort of a somewhat scaled down version of this also recently appeared in the notices of the Annals. Okay, so I think I'll stop here. Thank you.
Thank you, Igor. Thank you very much. Very nice. All right, I think it's time to have the next talk. It is a great pleasure to introduce Jason Bell, who will tell us about Specht's problem and decidability.
Okay, well, thank you for the opportunity to speak here. It's a real honor to speak at Amitsur Centennial. I think every ring theorist can say Amitsur is a big hero. And when I was a grad student, Lance Small had some AMS points, and he used them to buy me the collected works of Amitsur, and I still cherish these 20 years later. So anyway, I should get started. So some of my students might be watching, and they might not know this, so I'll just recall that a ring satisfies a polynomial identity if there's a non-commutative polynomial. This is the free algebra, so the variables don't commute, such that whenever we plug in d-tuples from our ring, we always get 0. And of course, commutative rings satisfy this identity, Wagner's identity, maybe it's Wagner-Hall identity, I don't know. M2Z satisfies this funny identity. And if one of these polynomials is not an identity, if a ring doesn't satisfy a certain polynomial identity, we'll say that that F is a non-identity. So one of the really big results, one of the great results in PI theory is this K-Mer solution in characteristic 0. And basically what it asks is, if you have a ring satisfying a polynomial identity and you look at all the identities that it satisfies, you'd like to know if maybe you can deduce all of the identities just from a finite set of, start with a finite set of identities, and then by doing substitutions, applying endomorphisms, whatever, if you can recover every other identity. And so this is what's called being finitely based. And it's actually a very hard to find it written down, or at least it was. Now there's this paper of Eli and Alexei Belov and Jakub Karasek that really fleshes out the details and makes it understandable, or at least understandable to someone more like me. But a key component of K-Mer's work is what's called the affine representability theorem. And what we have here is we have this finitely generated algebra that satisfies some polynomial identity. And so it's going to satisfy a set of polynomial identities. And what it says is that after possibly extending the base field, we can find a finite dimensional algebra that has the exact same sets of identities and non-identities. So somehow a finite dimensional algebra witnesses everything that the original algebra A witnesses. And what's relevant for this talk is that since K-Mer's work, so a lot of the work was done by Alexei, but recently Alexei and Louis Rowan and Uzi Vishny have collaborated to write a series of papers. And these are very non-trivial, difficult papers that extend K-Mer's theory to commutative base rings. So this work really relies on their work in a strong way. And I wanted to look at what affine representability is saying. So what we can think of it as saying is that if you give me some set of polynomial identities and some set of non-identities, then it says that if there's an algebra for which the set of the things in S are identities and the elements in T are non-identities, then we can witness it with a finite dimensional ring. So there's a finite dimensional ring that witnesses this fact. And one of the things that I was curious about was whether there might be a finitary version of this. So here, the question is, now we have sets S of identities and a set T of non-identities, and we're going to insist that T be finite, and I can explain why soon. But we want to know if there's an algebra which satisfies all the identities from S and doesn't, and everything in T is a non-identity, then can we actually witness it with a finite ring? So this is in the same spirit of as affine representability, but now instead of a finite dimensional witness, we want a finite witness. And I mentioned that we had this hypothesis that T needs to be finite. And the reason for that is you can see that any finite ring will always satisfy an identity like this. This is just the pigeonhole principle. But here is a commutative ring that's infinite that doesn't satisfy any such identity. So if I allowed T to be the infinite set of all non-identities here, or all identities here, then I could never find a finite ring for which every element of T is a non-identity. Okay. So this is obviously an obstacle, and in terms of the spirit of Specht's original problem, it's obviously shows that you really need finite dimensional to do the full Specht. But in many cases, you're actually only interested in finitely many identities and non-identities. You're interested in finite sets. So in that case, it is still a natural question to ask whether we have this finitary version. And you might say, well, why? Finite rings and finite dimensional rings both have nice structure theory, but the structure theory of finite rings is still slightly nicer. So we all know that if we have a finite ring, again, some of my students might be here, so I'll just recall, if we have a finite ring, it always has a nilpotent Jacobson radical. Well, that's still true for finite dimensional rings. And then when we mod out by the Jacobson radical, we get a product of matrix rings over finite fields. That's not true, obviously, for finite dimensional. And there you get division rings. And so then you get into questions about Brouwer groups and things like this. So it's still nicer to work with a finite ring. So let's just look at an example. So I used to teach, I teach classes on ring theory, and students always really love the commutativity theorems. And one thing Lance always told me was he just didn't like commutativity theorems at all. But they're still so much fun to teach. And one of the big theorems that's fun to teach is this Jacobson theorem. And I'm going to look at the bounded version, which just says if a ring satisfies the identity x to the n equals x, or n is bigger than or equal to 2, then it's commutative. It's still a hard theorem, even in this bounded version. But for finite rings, it's almost trivial once you have the structure theory, because you can see. I'm trying to admit Alexi. You can see that if you have x to the n equals n, you have no nilpotent elements. So that means your Jacobson radical is 0. And so that means your ring with this. And because matrix rings have nilpotent elements, we know that we have to have 1-by-1 matrices. So we're a product of fields and we're commutative. So just as a general principle, proving commutativity theorems and things like that is easier for finite rings, much easier than it is for infinite rings. So even proving this bounded version for Jacobson is hard in the non-finite case, right? You need a generalization of Wedderburn's theorem that Jacobson did. You need to use Jacobson density theorem. You know, there's a lot of machinery that is involved. It's not something you could just write down unless maybe you're Jacobson. But notice that the finitary version of affine representability allows us to deduce the bounded version of Jacobson from knowing the finite case. And here's the proof. I've written it here. It's pretty straightforward. Suppose there's a non-commutative ring that satisfies this identity. That's the Jacobson identity. Then what we're saying is that x to the n minus x is an identity. And we're saying xy equals 0 is a non-identity because we want a non-commutative ring. Then it says by finitary version of affine representability theorem, if we knew that, that would give us a finite ring for which the Jacobson identity holds, but it's not commutative. And we just showed that can't occur. So knowing the finitary version of affine representability could give us a quick proof in that sense. So here's a theorem. I attribute it to me and Peter Danchev and Alexei Belov, Kennel, Louis Rowan, Uzi Vishny. It's really, though, it's two separate results. And the real result is here. And then this is kind of saying, okay, we can observe from their results that we get this. It's affine representability, the finitary version. Let S and T be sets of polynomial identities with T finite. So T will be a set of non-identities. So if there's a ring that witnesses the fact that S is a set of identities for this ring and T is a set of non-identities, then we can actually find a finite ring that witnesses this fact. And like I said, Alexei and Louis and Uzi proved a version of the affine representability theorem for commutative base rings. So in fact, we're going to use it for Z, commutative Noetherian base ring. And they show that these sort of, if you model it by a T ideal, which is just all the identities, you know, the ideal generated by all the identities of the algebra, you can embed it in a matrix ring over the complex, over a commutative ring. And that is enough for us to deduce the result. So, and I should mention that one important case, at least historically, is commutativity theorems. And there you're asking if you have a set of identities and you want to know if XY is a non-identity, can such a ring exist, right? We want to say, if we have a ring satisfying these identities, is it necessarily commutative? And another way of saying that is if we have a ring satisfying these identities, and this is a non-identity, does that mean the ring can't exist? And what this allows us to do is it allows us to say, okay, we can limit our search to finite non-commutative rings. Is there a finite non-commutative ring satisfying these identities? And like I said, Lance sort of drilled into my head that commutativity theorems, you know, he always said he didn't need a theorem to tell him a ring was commutative. But I think he would maybe say maybe something like Sen's theorem or something is a nice commutativity theorem, but maybe not much else. But this is really sort of a theorem about will be a theorem about decidability, saying we can decide whether we have a commutativity theorem. So in that sense, I still think it's kind of nice, and at least appropriate for the conference, because Amitsur, of course, did a lot of stuff on polynomial identities. So here's our theorem. Let S be a set of polynomial identities. If there's a non-commutative ring for which the elements of S are identities, then there's a finite ring. So that's just the observation we made. And this will give us a general framework for approaching commutativity theorems of this form. So these are all sort of first order statements, right? We're not doing the unbounded case. We've got a finite set of fixed polynomial identities, and we want to know, does that imply the ring is commutative? And the strategy now is we prove it holds for finite rings, that finite rings, where we have this nice structure theorem, we can deduce the result, and then use the finitary version of affine representability to deduce the theorem to the result for all rings. So that's the strategy. And I mentioned that there's decidability, and I do have a plan to sort of implement this on a computer, or at least to get someone to help me implement this on a computer this summer. That will hopefully be useful for teaching, but I want to talk about how we actually prove this for finite rings. So to help with the question of finite rings, we can restrict our search to what we call minimal non-commutative finite rings. So these are rings where every proper subring and every non-trivial homomorphic image, every proper homomorphic image becomes commutative. And because if you have a ring that satisfies a set of polynomial identities, since that property is inherited by subrings and by homomorphic images, if you have a finite ring, that's a counterexample, you can always find or that's an example of a ring that satisfies the S identities, you can always pass to a minimal one. And the question is, can we classify the minimal non-commutative rings? And I initially thought this was going to be an easy thing to do. As it turns out, it's actually, I don't know what the answer is, but we can give sort of a coarse taxonomy of the minimal non-commutative rings. So here's the first example you come up with if you look for a minimal non-commutative ring. You look at the upper triangular matrices with entries in a finite field, then this ring is non-commutative and it has size p cubed. And any unital ring of size p squared will be commutative because one is in the center and it's going to commute with another thing in the basis. So we can see that these rings are minimal and they're non-commutative rings. So this is our first class, and we have a nice description here. And like I said, can we classify it? We don't know. I would like to know a classification. But I do say that if we had a classification, then we could limit our search to just checking among the finite non-commutative rings. If you give me a set of polynomials, identities, and ask, does this force commutativity? Well, I could just, like I said, it suffices to check for finite examples, finite non-commutative examples. And then I said it in fact suffices to check for finite minimal non-commutative examples. So if we could somehow classify them, it could limit our search. So I want to just give our taxonomy of minimal non-commutative rings, and we already saw this family of UPs. Here's another family. It's sort of a twisted version of UP. I take a field FQ, which is FP to the N, and basically I twist by a power Frobenius along on this entry. And this ring, it will be non-commutative and minimal for some values of N and I. It's not always minimal. It's not always non-commutative. Well, I guess it's always non-commutative. It's not always minimal though, but it at least limits our search. We didn't decide to look any further than this, but this is at least some minimal non-commutative rings lie on this list. And then here's sort of the miscellaneous class, but it's still kind of understandable. So if you give me a prime P, I'm going to let this AP denote the class of non-commutative rings, basically that are isomorphic to a homomorphic image of a two-generated ring, where basically I make the commutator ideal nilpotent and annihilated by anything in the homogeneous maximal ideal xy and the prime p. And Jn is the ideal xy p to the n. So basically, we're just saying we have a nilpotent Jacobson radical that's generated by x, y, and p, and the commutators are annihilated by the Jacobson radical. And it has to be some homomorphic image of that. We don't know which homomorphic images are minimal, but maybe it can be classified. Anyway, it's not so important. So this was our theorem. This started because Peter wrote me asking me if I could prove certain things were identities. And then I started to use the strategy and think maybe we could do it just to give a general decidability procedure. And that led us to classifying the finite non-commutative rings. So the minimal non-commutative rings are either the UPs, the sort of twisted by Frobenius version of the UPs, or one of these algebras in AP, which we don't understand. And this is a sort of coarse taxonomy of the minimal non-commutative rings, but it's at least telling us where to look if we're trying to prove these polynomial identities force commutativity. It says it suffices just to check on these rings whether the identities impose commutativity. So here's perhaps the more relevant statement. If S is a finite set of identities, and if we can't find any ring in these three classes that satisfies all the identities from S, then that means that we have a commutativity theorem, that if a ring satisfies all the identities from S, then the ring is commutative. And S is commutative. Actually, that sentence is okay. And I just said why, so I won't repeat myself, but basically it just comes from everything we've been saying, right? Using the finitary version of affine representability and using the fact that there's a minimal example. And let me just quickly show bounded Jacobson and revisit it. If n is greater than or equal to 2, and like I said, this is all applying to just first order statements among rings, so we can't do anything in the non-bounded case. If R is a ring satisfying this identity, x to the n equals x, R is commutative. Well, the proof is that if there weren't, there would have to be a ring from one of these classes that satisfies this. And these rings all have a non-zero nilpotent commutator ideal. And we saw that if you satisfy x to the n equals x, you have no nilpotent, no non-zero nilpotent element. So that's the proof right there in that case. So what I was kind of interested in, I've been working with my friend Rahim Musa on a lot of decidability procedures. He's a model theorist, and we were thinking about can we decide the rank of an elliptic curve and characteristic P and all these sorts of things. And it sort of got my head into thinking about decidability procedures. And just this question where you input a finite set of identities, and you'd like to know if there's a finite decision procedure. So there's an algorithm that runs, and after finitely many steps, either tells you that any ring satisfying these identities is commutative, or it spits out a counterexample. It spits out a non-commutative ring that satisfies all these identities. So that was sort of what we were interested in. And like I said, it terminates after a finite number of steps. There were, if you look at the literature, there were these sort of what are called semi-decision procedures. So they may or may not terminate, but if they do terminate, they give you an answer, but they're not guaranteed to terminate. So this has the pleasant feature that it's guaranteed to terminate after a finite number of steps. And really, this can be thought of as three algorithms. So three separate algorithms. So basically, we have an algorithm for UP, an algorithm here, and an algorithm for the class AP. So for each class of rings, we have an algorithm that takes as input a finite set of identities, and it answers, okay, is there a ring in this class that satisfies those identities? And it will either output such an example, or it will tell you that no such example exists. And I'll show you how the procedure works for the class UP. That's sort of the easiest class. The other two are trickier. BPNI isn't so much trickier. We need Alon's sort of combinatorial Nullstellensatz to sort of give us some effective bounds that can allow us to deduce the algorithm terminates. And this class on AP is actually sort of a tricky one, but it also terminates for reasons I can explain. So let me just show the decision procedure for UP, because it's kind of the easy case. So you give me as input a finite set of polynomial identities. And I'm going to say, is there some prime P such that these are all identities for UP? And remember, UP is just the set of upper triangular matrices with entries in FP. And so this is actually the easiest algorithm. What we're going to do is we're going to let X denote the set of 8 upper triangular matrices with 0, 1 entries. So I've got these 8 matrices. And I didn't say this was an efficient algorithm. I just said it terminates. So the first step is that for each S tuple, so we have 8 to the S tuples, we evaluate each of our identities on these S tuples. So these identities involve S variables. So we're plugging in the S tuples. Of course, if one has fewer variables, we just assume that it's in S variables, but where none of the other variables occur. So we have a few cases. What we could have is that the PIs all vanish for every I and every tuple. And that means that it's going to be an identity for U2, because the elements of X to the S, the elements of X, their images actually span all of U2, right? F2 just has 2 elements. So the elements of X are going to span U2. And that means that when we pass to the homomorphic image, these will be identities for U2. So if not, if we get these vanishing, we can return U2 as output and say, okay, here's an example. So if not, we're going to go to the next step. And what we've done is we found some S tuple and some identity that doesn't vanish. And we compute the GCD of the entries. And if the GCD is 1, then you can show there's never a prime such that these are identities, because you're always going to be able to plug these in FP, and you're going to get a 1 in one of your entries, or you're going to get entries with GCD 1. So otherwise, D is bigger than 1, and we go to the next step. And we factor D, which can be done in a finite amount of time, and we get the primes that divide D. And then we know that if P1 through PM are identities for UP, well, they all have to vanish. They can only vanish mod a prime divisor of D if we're looking at primes. So for the primes P is necessarily in one of these sets. And we basically now got a finite set of finite rings, and you can just by brute force check. I'm not saying it's a great, an efficient algorithm. I'm just saying we have an algorithm and we like to speed it up. But for a finite ring, you can explicitly check whether a finite list of things is an identity in a decidable way just by looking at all S tuples in the ring. And since we only have a finite number of rings left to check, we get the result. So the algorithm is a bit long to perform if it were to be coded into a computer the way we suggest doing it. But in practice, we would often just use ad hoc methods. And it was incredibly fast for a lot of things. So probably the algorithm can be sped up. But I'll give an example of an identity no one would ever care about, I don't think. So this is the identity x squared y squared plus x to the 4th y squared plus xy xy. This, if you satisfy this identity, you're commutative. And the first step of our algorithm is you rewrite the polynomial mod the commutator ideal. So you get something like this. And because it's not 0 mod the commutator ideal, we can plug in some integer and get something non-zero. And that tells us that 3 has to be 0 in our ring, if this is an identity. So if there's a non-commutative ring in our class of minimal rings, it has to either be U3, B3, and I, or a ring with A3. For U3, we can just find an example where we plug in and get something non-zero. For B3 and I, what we can do is we can mod the n by Alon's Nullstellensatz. So basically, when you mod out by the commutator ideal of one of these B3 Ni's, you get FQ, F3 to the N. And so this would have to be an identity for that. And Alon-Snell-Stallensatz version says, you know, a polynomial can't vanish on a big box. A polynomial of a certain degree can't vanish on a big box. So in particular, we can't vanish on FQ cross FQ if Q is big. So right away, we can use that to do this. And then for rings in A3, we can sort of use sort of Nagata-Higman type things to mod the index of nilpotence of the Jacobson radical and just check by hand in that case, because we've sort of narrowed down our ring. Let me do another example. So this was the original thing that Peter wrote to me about. He said that he mentioned that he had this generalization with Anderson, where he proved this result and with opposite parity. If you have two elements like this, and you have this sort of identity, then R is commutative. And he was asking me if there's some analog of Herstein. And you know, I have to admit, I wasn't so interested in that, but I started to think about, well, let me just try to work out the finite case, because that's what I would tell my students to do in ring theory when trying to prove something. And then started thinking about decision procedures, and it became a lot of fun to me. And well, it felt kind of relevant for the Amitsur conference too, and a big Israel connection. So so it made sense to talk about it here. But our decision procedure at least allows us to look at the bounded version of more general one variable polynomial identities. And like I mentioned, there's a related result to Jacobson's theorem due to Herstein, where Herstein looks at not x to the n minus x being 0, but x to the n minus x being central. So we can completely classify polynomials that impose commutativity. So there's a non-commutative ring R for which p of x equals 0 is an identity, if and only if p of x lies in this. And this just comes out of the decision procedure. And in fact, this condition is decidable as well. So there's an algorithm that will tell you if there's a prime p for which this holds. And if you want to know the Herstein analog, there's a non-commutative ring for which this is an identity, if and only if there's a prime p for which the derivative lies in this idea. And again, these are completely decidable conditions, but you can see that for something like x to the n minus x, you can never lie in one of these ideals. So you get the bounded Herstein and bounded Jacobson. Again, I mean, probably done it like 10 times now. And this was something Peter was interested in working out. So we have this theorem. And I think he's actually interested in the unbounded version more than this. So if A and B are positive integers, a ring satisfying this is commutative if and only if one of the conditions hold, B equals 1. So that's Herstein. Or the GC if A and B is 1 and A and B have opposite parity. And this doesn't give the unbounded versions. Like I said, everything is sort of in the realm of first order logic that we do. But it's at least suggests what they should be. So here's a question, and probably I should attribute this question to Danshev, and I think he'd be very interested in knowing the answer. Suppose R is a ring, and for every x there exists positive integers A and B, and I guess I want A bigger than B, such that x to the A minus x to the B is central, and either B is 1 or GCD of A and B is 1, and A and B have opposite parity, so just like we had in the unbounded case, then that should imply R is commutative. How am I for time? I was going fast because I was worried about running out of time. I think I'm supposed to end a little before 1 maybe. So let me just, oops, I went too far. One of the good things about the pandemic, I guess there are some good things about the pandemic. One of them was I was teaching online, and they made us, well, I don't think they made us use, they gave us this platform called Piazza to sort of make the students feel like we were in touch with them all the time. And they were writing, 24/7, but it basically made my life a living hell, actually. But it was, I look back on it fondly now. But the students, one of the students, I happened to be teaching rings and polynomial identities. because I could teach whatever I wanted, basically. And a student just asked me this question: is x y to the n equal x to the n y to the n force a ring to be commutative? And well, I'm not an expert on these commutativity theorems, and so I looked up the answer. You knew it was going to be someone like Jacobson or Herstein or someone. And Herstein had in fact considered these rings, and his result was he showed that the commutator ideal is necessarily nilpotent. The reason is that you don't actually get a commutativity theorem in general. In fact, you can get rings in our class FP that don't work. So you get something like XY. You can get counterexamples like this for certain values of n. And then I started to wonder, well, maybe we can revisit Herstein's result using the decidability procedure. And let's say we have a subset of the natural numbers, and we suppose that we satisfy this identity for every n and s. And when does that impose commutativity? Well, it turns out that you can get a non-commutative example if and only if you can find a prime p such that p divides n choose 2 for every n and s. So somehow that's the result. And I don't think this would be so easy to prove without the decidability procedure. So basically, you just run the decidability procedure, and it will more or less just tell you this. Of course, you have to do some ad hoc stuff in a few places because of S being infinite, but this is basically the idea. This is proved by applying our algorithm. Well, I noticed in the same paper, Herstein also considered identities like this, and he proved the same thing, that the commutator ideal is a nilpotent ideal. And we can again ask which sets S can we find where, if we satisfy this identity for every n and s, does that force us to be commutative? And it turns out this really comes down to the Frobenius action. If you have a set of natural numbers, if you have a non-commutative ring that satisfies this identity for every n and s, this can only be done if s is contained in the powers of p, when p is bigger than or equal to 3, or when s is contained in the powers of 2, starting at 4. And again, this is just kind of the Frobenius action, and really the relevant counterexample again is this ring. And the fact that you need a cube here is explaining why the 4 holds. So I want to give one last application, and wow, it's Amysur's conference, so I should mention Amitsur Lubotzky, certainly, in the realm of polynomial identities. Anyone who studied polynomial identities knows that the most important class are the homogeneous multilinear identities. These are the things that allow you to show that being PI is preserved under base change. You know, this is sort of the really important thing, and you do this linearization procedure. You might need an infinite field or something like that to get it to work, but it's still showing that these are relevant. So of course, it's a natural question to ask, when does a set of homogeneous multilinear identities force a ring to be commutative? When do we get a commutativity theorem? Oh, and that's what I asked here. When does a homogeneous multilinear identity force commutativity? In fact, I'll answer it for a set, possibly infinite set. So here's our theorem. Hopefully this shows up. Let S be a set of homogeneous multilinear polynomials. And we want to know, is there do we get a commutativity theorem? So I'll look at the other phrasing it differently and ask, is there a non-commutative ring that satisfies all these identities? And all the identities have to be of this form, they're homogeneous multilinear identities, so they're basically permuting the variables. And what happens is you can look at a prime P and you plug in P1111, so that's just the sum over all the C sigmas. So if P divides that, and if P divides this funny quantity theta ij, which is basically just counting the sum over C sigmas where we have an inversion between I and J. I'll admit this guy. If this happens for every C, if this happens for every identity for some fixed prime, then there's a non-commutative ring. And in fact, there's a very nice non-commutative ring. It's this, which I think is minimum. I didn't check, but it must be, I feel. Okay, so if there's a prime P that if this holds, then this ring will witness it. And as an example, here's one identity. Is there a non-commutative ring that satisfies this identity? Well, the answer is yes, because you plug in P11, you get 6. And if I compute these theta ij's, well, exactly half of the terms will have an inversion between I and j. So you'll get 3 for each of them. And so there is a prime that divides all these quantities, namely the prime equals 3. And so in particular, this ring will satisfy this identity. So there's an 81 element example. This is my most Israeli paper ever, except that I don't have any Israeli co-authors on it. I guess I probably do have papers with Israeli co-authors. Yeah, I do. But other than that criterion, it's my most Israeli paper ever because well, I'm speaking at the Amitsur conference. It uses the Beloff, Canal, Vishny, Rowan paper, and we published it in the Israel Journal because we felt it was such an Israeli paper. But when we published it, the referee asked us a question and said, well, this ring is kind of the ring that's relevant in the context of proving commutativity theorems for multilinear identities, right? So the referee asked us the question whether we could find, we know the identities for this ring are finitely based. Can we give the identities that sort of generate the identities here? And this is a fun little exercise. These are all the identities for that ring, FP, U, V, odd, U squared, V squared. Wait a minute, was that the ring? U squared, V squared, U, V, yes. So these are all identities for them, and these generate the identities. I don't know if this is a minimal set of generators, but it's a set of generators. Anyway, that is my talk, so thank you.
Jason, thank you very much. That was quite interesting. Are there any questions?
I have a question.
Yes.
I mean, your talk is not a characteristic zero talk, but you know that Regev introduced the notion of exponent of an algebra.
Yeah.
And commutativity says exponent 1 or exponent 0. If it is important, it will be exponent 0. And there is a notion of minimal varieties. That is a variety that if you go to a subvariety, you drop down the exponent. Okay, so I mean, I don't know characteristic P. Belov knows characteristic P and Louis and Lucy. But maybe you can extend to more general situations. In other words, not to commutativity, but to go down in exponent.
Yeah, so yeah, I think that would be nice. I mean, I think anything that's sort of first order, you know, somehow expressible first order, maybe there is some decision procedure in this context. So yeah, that would be a natural thing then to look at exponents. I hadn't thought about that, but actually that might be more useful even so. Yeah, I'm not sure.
So the references are Antonio Giambruno, but yeah, you know that.
Yeah. Yeah, I'll check it out. I didn't make the connection, so no, that's very nice. Maybe I can talk to you about it at some point.
Any other question?
I enjoyed the talk.
What's that?
I enjoyed the talk.
Oh, thank you. Yeah, it really, I gained a real healthy appreciation for all the work you've done on Specht. Is that Alexei?
Yeah.
Yeah.
Happy to hear this. And when do you have some reference?
Yeah, I can send it to the chat. I have to figure out how to do that, but let's see. I mean, I guess I can do that after the talk. I can put it.
Yeah, I would be happy about all of this stuff, and I'm happy that all the subject is pretty live. And I enjoyed it.
Yeah.
Okay.
There is
Thank
a
you.
classification of minimal groups, finite groups.
Yeah.
Of the same type. Is that relevant here? Does that help?
I don't know if it's relevant. I mean, probably it's the same spirit of how the argument goes. Yeah, I don't know. I mean, is there a classification? I guess there can't be a classification of minimal Hopf algebras or something like this. Yeah, I'm not sure. I mean, I did come across this whenever I was doing Google searching, for groups. So, and I think there's probably some connection in terms of how the arguments go. But yeah.
Any other comments or questions? All right. Thank you, Jason. So it is my pleasure to introduce Danny Krashen, who will tell us about splitting fields of central simple algebras.
All right, thank you. I'm really grateful for the opportunity to speak at this event. It's nice to see everybody, even virtually. Yeah, so today what I'm going to talk about is actually joint with Max Lieblich. And you know, this is on a topic which some of you might have heard a little bit about before, although there's maybe some refinements of the result at the end, and I'm going to kind of emphasize different parts. Actually, it's closely related to Igor's talk, so I'm kind of grateful that he kind of set the stage a little bit. The basic question that we want to ask is just as follows. So given a central division algebra, D over some field K, broadly speaking, and I'll refine this question, we want to know which other algebras have the same splitting fields. Well, I mean, there's the kind of obvious answer, which Igor actually gave. So a very well-known result of Amitsur says that that if you allow all possible splitting fields, then only only the other generators of the cyclic subgroup of the Brouwer group generated by D do. So that is to say, if you let, let's say, K of D be the generic splitting field, of D, so this is actually the function field of the Severi-Brouwer variety of D. So in particular, this field has transcendence degree, it's a central division algebra of degree n. So this has transcendence degree n minus 1. Then the algebras which are split by that field extension are exactly those in the cyclic subgroup generated by D. So, so there's at most a finite number and a very kind of restricted class of algebras that have the same splitting fields. But so so if you recall in Igor's talk, it then became a natural question to say, okay, well, if we consider all splitting fields, then this kind of puts far too much constraint on the algebra. Maybe we might ask which other algebras have the same finite splitting fields. And so in that case, if one were to restrict to finite splitting fields, then of course, the answer really varies with the ground field. And so, for example, one finds for various classes, as Igor kind of elucidated, for K, let's say, finitely generated, for example, then you get that there's going to be a finite. So this is from Chernosov, Rapinchuk, for example. There's going to be a finite collection of algebras with the same finite splitting fields. As D. But on the other hand, for K general, for a general base field K, one can find examples where where there exists, let's say, D1, Dn, kind of an arbitrarily large collection of non-isomorphic algebras with exactly the same collection of finite splitting fields. I.e., to be a little more clear, there exist K and the Ds as above. So the fields that come up in this context are, very far from finitely generated. They're very kind of infinite fields, where one is kind of adjoining points on kind of generic points on function fields of lots and lots of varieties, kind of iteratively, in a kind of Merkurov construction. So on the one hand, there are, if you look at finite splitting fields, so for some fields, that determines everything, but in general, you can have arbitrarily large classes with the same finite splitting fields. On the other hand, if you let yourself go all the way up to the transcendence degree -1, you cut yourself down to a single algebra. And so it makes sense to ask about all the numbers in between. So for example, what if you have algebras with the same transcendence degree 1 splitting fields, for example, or the same transcendence degree 2 splitting fields? Does that imply that the algebras generate the same cyclic subgroup? Are there going to be a finite number of algebras that have those common splitting fields? Kind of how do we kind of classify that? Okay, so what about, question, for an arbitrary field, by the way, I apologize that I'm like not well organized enough to have actually had slides. I hope you guys can actually read what I'm writing. Is it all good so far?
Very good.
Okay.
It's good.
Okay, good. Then I'll let myself relax and the writing will degenerate now, but I'll try not to. Okay, for an arbitrary field K, you know, and some central division algebra D over K, you know, we could let's say define, for example, let's just say the genus sub I of D to be the set of central division algebras D prime such that D and D prime have the same collection of splitting fields of transcendence degree less than or equal to I. Okay. So so the above says that that genus sub 0 of D can be infinite for general K. On the other hand, genus sub n minus 1 of D is going to be simply the cyclic subgroup generated by, you know, the set of, you know, all right. Let me just abuse notation and say the set of, you know, Brouwer classes, division algebras, whatever, in the same cyclic subgroup if n equals the degree of D. So then we can ask, let's say, what about genus sub 1 of D, right? Well, of course, there's like a silly case, which is that D happens to be a quaternion algebra, in which case, you know, this is just going to be D itself. So, you know, if degree of D is 2, then it's just D. But now let me go ahead and state the results. So there are kind of two theorems. On the one hand, so these are both myself and Max Lieblich. So we can find fields K and collections, well, and central division algebras D over K, degree of D equals n bigger than 2, but, you know, for all such n, you know, let's say for any n at least 2, such that the things which have the same transcendence degree 1 splitting fields as D is arbitrarily large. You know, it's like whatever cardinal you want. Okay, so this can be, so just like in the finite splitting field case, transcendence degree 1 splitting fields aren't enough to you know, to distinguish algebras in general. On the other hand, so as above, given yeah, so given any field K, let me say any field K of characteristic 0, and D over K central division algebra. The genus 3 of D is just D. And in fact, if K is uncountable, the genus 2 of D is that big. So the punchline is, sharing all the same transcendence degree 1 splitting fields isn't enough, but if you share the same transcendence degree 2 splitting fields, that always determines well, it determines it if you're uncountable, actually, and and in general, let's see. Let me put this as an extra proviso in here. The two genus is always finite for characteristic 0, but if it's an uncountable field of characteristic 0, it's actually just the cyclic subgroup.
Does
All right.
arbitrarily large mean infinite?
Yeah, it means whatever cardinal you'd like. Yeah. Yeah. So, yeah, in fact, the way the argument basically goes is like, if you choose K and let's say D is some arbitrary collection of non-isomorphic central division algebras of period equals index equals n, then there exists an extension K prime over K where these algebras such that all algebras dk prime for D and D are non-isomorphic with the same period equals index equals n, and they all have the same transcendence degree 1 splitting fields. So if you start with any collection of non-isomorphic algebras over any field, you can always lift up and force them to have the same transcendence degree 1 splitting fields. So yeah, they can be this. So this class script D can be as large as you want it to be. Okay. So the kind of outline of what I plan to say is first off, kind of just a little bit about how to describe Brouwer classes split by transcendental extensions. So there's a couple of different ways of thinking about it, and it'll be useful to kind of explain how that works. And then I'll describe, the first theorem, the transcendence degree 1 case, and then the transcendence degree 2/3 case, at which point I'll probably run out of time. It's good to plan ahead and know when you're planning to run out of time. So that's what'll happen. All right. So first off, how do you describe splittings of Brouwer classes? So so kind of part one or whatever. So given x over k, a smooth projective variety, we'll just talk about how to describe the elements in the relative Brauer group, k of x over k, which is to say simply the kernel of the map from Brauer of k to Brauer k of x. So of course, our goal is to describe algebras with the same splitting fields of various transcendence degrees, and so therefore it's natural to ask, well, what algebras are split by transcendental extensions in the first place? Okay, so so how does that work? Well, I'll just also mention that I'll just say. So one way to describe this as follows. Given your x over k, you can consider the associated Picard scheme, whose points are isomorphism classes of line bundles, let's say L on X. Well, L on X at the say separable closure. I'll write a K bar, but really separable closure, such that the isomorphism class is Galois invariant. So that is to say, it's kind of clear, the notion of what we think of as the Picard scheme is exactly what we think it is at the algebraic closure. It's line bundles on this geometric thing, xk bar. The problem is, that's not the same, so I guess I should say the Picard's, right. So points of the Picard scheme are not exactly line bundles, though points of the Picard scheme are isomorphism classes of Galois invariant line bundles. Okay, so given, let's say, the isomorphism class of L as above, you might try to ask, you can ask if L comes from an actual line bundle, I don't know, script L on X. So i.e., is L isomorphic to something brought up to the algebraic closure, actually an honest line bundle on X. And if you wanted to do this, you generally would do this kind of thing by descent, trying to glue together these isomorphisms, of the different Galois conjugates to an actual Galois action on the line bundle itself. But in general, you can't do that. So the obstruction, if you just tried to write it out very explicitly, to descent data on L, which would give an L as above, is a 2 cocycle, which you could, I don't know, say beta, which gives you something actually in the no, it's a in H2 of in terms of the Galois action, so it's a K, and just GM, the GM kind of being global automorphisms of a line bundle, since X is projective. So the obstruction for a line bundle to actually descend is a Brouwer class. And so you actually get a natural map that goes from the Picard scheme to the Brouwer group, where this L isomorphism class of L maps to this beta, in which case we say that L is a beta twisted line bundle on X. That is to say, a beta twisted line bundle is not actually a line bundle on X. It's a line bundle at the separable closure for which beta is the obstruction to actually giving you a line bundle. And the significance of this is that it turns out that this map, the induced map from here to there, describes the relative Brouwer group. So this fits into an exact sequence. Take X of K goes to Brouwer, K goes to Brouwer, K of X. And so in particular, this exactly surjects onto the relative Brouwer group, being the kernel of that map. And so this is one way to describe what classes are split by these transcendental extensions. In fact, these betas fit together to give a Brouwer class, which is sometimes called alpha X, in the kind of geometric Brouwer group of the Picard scheme itself. And one can actually think about, therefore, this map as taking some point here to this geometric Brouwer class, kind of restricted to the point. So that's going to be a useful way to think about it. All right, and that is our description of what it means to have geometric splitting. Okay, so now let me give from this kind of based on that, let me give a very brief kind of outline of where these theorems come from. Okay, so first, the first theorem that I want to remind you of is that so if degree of D is bigger than 2, we can make a field extension. So this is some D over K, some field extension K prime over K, making the one genus of D larger and larger. Well, this isn't really how I stated the theorem, but so the actual theorem, well, let me just go back, was that we can find fields and division algebras of a given degree at least 2, such that these one genus, the algebras that share the same transcendence degree 1 splitting fields, is arbitrarily large. But as I said, the method of doing this is going to be, we start with an arbitrary collection of non-isomorphic central division algebras, with period and index being in. And we are going to make an extension that forces all of their splitting fields of transcendence degree at most 1 to be the same. So what I really am going to explain is what you might say is kind of the induction step. So actually, let me say, suppose you have two algebras so D prime and D both have period equals index equals n, bigger than 2. Then the basic step, maybe I'll call this a lemma now. Then I can find k prime over k such that the index of D prime over k prime is equal to n still is equal to the index of maybe I'll say period, because that's what we've already established. We've already started with the fact that period equals index. So I just want to make sure the periods don't change. And and I guess I should have said this a little bit differently. Okay. Let me now restate this in a way that's grammatical and actually will work better. Yeah, so I should have had slides, right? I'm sorry, but let's try it like this. So given D prime and D over K with period equals index at least 2, and let's say L over K, a transcendence degree 1 splitting field for D, then I can make a field extension K prime over K. I guess I don't need to repeat myself, such that the period of these things doesn't change, and such that L K prime splits D prime as well. So you have your two algebras D and D prime. You want them to share all the same transcendence degree 1 splitting fields. You have a transcendence degree 1 splitting field over here, but maybe it doesn't split D prime. But then if you extend to some bigger field, then you make it so that this splits both of these algebras. Okay, so that's the idea. Now, if you grant that, the only obstruction to kind of like to getting the theorem is basically just a whole bunch of transfinite induction, and then that's so this is really the kind of key step. And I guess I should say that this is, let me just make this regular so that we can separate the kind of finite stuff from the transcendental stuff. So there's kind of there's another step there, but it's kind of easier to imagine this case first, the kind of geometric case. Okay, so what's the flavor of how it works, of how this lemma goes? Did the lemma actually make sense? Are there any questions about that? Because I did kind of restate it 8 times and it got a little confusing probably, but.
Go ahead.
Okay, good. So, all right. So proof, quote unquote. So if L is transcendence degree 1, so let's say L is the stuff split by the fraction field of some x where x over k is a curve. Now, of course, the curve is going to be, so the curve, by the way, will have genus at least 1, because if it had a genus 0, it would be a Severi-Brouwer variety. And these algebras are not split by Severi-Brouwer varieties because they have index bigger than 2. Sorry, Severi-Brauers they're not split like conics, which are Severi-Brauers of quaternion algebras, because they have index bigger than 2. So, so by the way, the genus of X is at least 1. Okay, but now, so what we know is that by the previous explanation, by what I said previously, the fact that K of X splits D says that there exists some point on the Picard scheme such that the image in the Brauer group, so here I have P and it maps to this Brauer class restricted to P, and that is going to be the class of D. So that's the statement, really, that K of X splits D. It means that, i.e., X has a rational point, let's say, P, which sits, so the Picard scheme, has a bunch of components to it. So maybe this is sitting on, the component of degree D for some D of pic X, some point there. And such that this Brauer class alpha X, when I restrict it to the point, is my D. So now I want X, K of X to also split D prime. So what do? You go to let's call it L equals the function field of K of X. Okay, so when you go to the actually the function field, excuse me, of pic dx first. So the function field of pic dx, you get a kind of a generic point, eta in pic dx of L. Let me mention that, by the way, that L over K is going to preserve indices and period, because pic dx has a rational point. So you're not going to split any algebras. You're not going to get new points on varieties that didn't already have points, because you're adjoining. You're going to the function field of variety that has a point on it. Okay. So so you get a generic point over. So what do you? So according associated with that generic point, you get a Brauer class, which is this alpha X restricted to the generic point. And the main point is that this is in the Brauer group of L, but it's really not coming from the Brauer group of K. So it's like a new Brauer class, that arises in this extension minus. So now the idea is we go to the generic splitting field of this thing minus the class of D prime. So when you've done that, so in other words, I'm formally just forcing this Brauer class to be D prime. This generic splitting field is not going to split any other algebras from, it's not going to split any algebras over K, because basically by assumption, because this is not coming from K, you can show that this thing isn't, the cyclic subgroup generated by this guy can't actually bump into the Brauer group of K. So again, we have this injectivity. Where did I have it? Yeah, as the going to the function field of this generic splitting field doesn't change the period or the index of D or D prime, but now the class of D prime is in the image of pick D x of L, well, L adjoin, if I call this thing E, L adjoin the generic splitting field of E. It's in the image of this into the Brauer of E. And so therefore, D prime becomes split. D prime becomes, split by X. Okay, so we can pretend that I gave an explanation of that. Let's pretend. And the other thing that, of course, I don't have time for, but maybe I'll say literally a couple words about, is this transcendence degree 2 or 3 case. So remember, the theorem is that if you, where did I put it? It's right here. So if we have a field of characteristic 0, then if you look at the transcendence degree 3 splitting fields, you only get the algebra, but even transcendence degree 2 splitting fields is enough. So this is kind of like Amitsur's result in some sense, that the only things split by that generic splitting field is the algebra. Well, you don't need to go all the way up to that transcendence degree n-1. You can just go up to transcendence degree 2 or 3. And the basic idea for theorem 2 is the Lefschetz hyperplane theorem, or Noether-Lefschetz in the dimension 2 case. Very roughly speaking, I'll just go over 30 more seconds, and then I promise I'll stop. It's really just coming from commutativity of the following kind of diagram. Lefschetz hyperplane theorem basically tells you that this is going to be an isomorphism where H is a linear, let's say X intersect H is a kind of linearly cut out, subvariety with respect to some, hyperplane and some projective embedding, or linear subspace of some appropriate dimension. You can get this thing to be an isomorphism, if X intersect H is dimension 3, or in general, or dimension 2 in the uncountable case. And the main point is that if you have a line bundle which is beta twisted, which goes to a beta here, then when you pull it back, it goes to the same beta. If X is the Savary-Brauer variety for D, then you chop it up with enough hyperplanes and you get some surface, say, where the Picard is generated by Z, is just generated by a single thing, like over here, and where the relative Brauer group therefore has to have the same generator. All right, let me end there. So thank you very much.
Thank you. Questions?
In the proof of the first theorem, how do you use the fact that X is a curve?
So I mean, right. I mean, basically what we're using is that the Picard variety, what are we, we want that the Brouwer class is really non-constant on the part of the Picard variety that we're on. So, it really came from this was the critical step, I think, that kind of, what we really needed was that the Picard variety, we had a point on the Picard variety which was describing the Brouwer class, and that part of the Picard variety wasn't just some points. If it was just some points, then it would be, if it was just an isolated point, then that would be, that would be coming, that would be, when we tried to go to the generic point, we would have just had something in the ground field. Okay, so the proof would have worked exactly the same if we were looking at varieties whose Jacobians kind of were positive dimensional. That's really always, or whose Picard varieties were positive dimensional, or Albanese or whatever, if you want. So in fact, we could make like a lot of more common splitting fields if, beyond just curves. The problem is just ones where the Picard variety is discrete. Those are the ones that this method doesn't get. I don't know I hope that answered the question.
Thank you.
Yeah, no. There are not many of those varieties whose Picard scheme is discrete, are they?
Well, I mean, no, not really. I mean, kind of most of the time, as you go like more general-ish or whatever, right?
Yeah.
You got stuff like, well, is that true? I don't actually, I'm
Okay,
saying that,
all
but
right.
it's not like I know geometry, so maybe somebody else should say something.
So you only need one component that's discrete for this argument to fail, right?
Yeah, you need that's correct, yeah.
True. And let me verify that what you did was you showed that there were transcendence degree 3 or 2, which actually the single fields had kernel just the cyclic group generated by D.
That's exactly right. Yeah. So in fact, I don't know if I didn't, maybe I didn't state that I could have stated that much better, in fact, right? So, really the statement is like, given D, there exists, we can call it like LD or something like that, which is transcendence degree, 2 or 3 over K, such that the relative Brouwer group of that is just D.
Right.
So it's like a single.
I might point out that the ones you constructed where you hit it with hyperplanes have discrete Picard scheme. You've arranged
Exactly. That's right. The proof fails for those.
Yeah. All right. Any other questions? Well, thank you, Danny, for a very interesting talk. And our festivities today are done, and we'll all see you tomorrow.
Okay, thanks.